We are now officially live for 3 hours of serverless, and I am really excited for the next 3 hours. So, hello everyone, my name is Jamie, and I am a developer advocate for a serverless cloud provider called Nimbella. And with me is Rodric Rabban, the CTO and a founder of Nimbella. And for the next 3 hours, we're gonna have him plus 4 other serverless experts provide sessions and Q&A for discussing a lot of different topics in regards to serverless technology. And before we go ahead and get started with those sessions, I do want to let everyone know that if you are participating in this conference, at the very end, we will be providing a certificate for everyone who has participated. So if you're interested in getting your certificate, stick around to the end and I will give you the instructions on how to get that certificate. So other than that, that is my opening introduction. Rodric, I will leave it to you.
All right, great. Thank you, Jamie. And thanks for joining us for what I think is going to be an exciting 3 hours of content. This program has something for everyone. And really what inspired this event is a lot of recognition that the future of computing in the cloud is serverless. And there's a lot of knowledge that needs to be disseminated for what is serverless, why is serverless the future, and the way we've organized this program is to give little bits and pieces for everyone. Those who are new, who have never heard of serverless, those who are curious, have dabbled in it and want to do more, people in research, in academia. There's some cutting edge research that will be discussed a little bit later. And if you're a pro, if you're an expert, we've got AWS heroes who have done a lot of consulting and have pro tips that they will share with you later. And I'm going to talk about at the end a little bit about Nimbella and how Nimbella is positioned to change the world in terms of serverless computing for everyone. Before we really dive into things, I want to extend a special thank you to several communities, individuals who helped us in supporting this event. We couldn't have done this without them in terms of spreading the word and getting the knowledge out. Thank you. I also want to recognize our speakers. We have 4 experts joining us today. Srushith, who is the head of engineering at KonfHub. Rob Allen, who is a software consultant and developer concentrating on HTTP and APIs. Professor Arjun Guha from Northeastern University, and Jeremy Daly. Jeremy is a serverless consultant and an AWS hero. And I'm also presenting today, and I'm going to have essentially a lay of the land initially, and then I will join you at the end to talk a little bit more about how Nimbella is changing the world with respect to serverless computing. Your serverless journey for today really starts with what is serverless? How did we get here? And then for the introductory parts, if you're new to serverless and you're curious about what is the power of serverless that you can actually wield, 2 great talks will set you up. After that, Professor Guha will talk about cutting-edge research that's happening in serverless, as I said earlier, followed by Jeremy Daly, and then I will conclude at the end, talking about how we're delivering the serverless promise to all developers. And why are we here really is this shift that's happening in the cloud, and it's being pushed from the top down and the bottom up. What I mean by the top down is that there's a need to actually change the way computing in the cloud is happening. And this need is driven by a recognition that in just a few years on the horizon, there will be millions of jobs that can't be filled in the US alone. If you just look at the people who are coming out with graduate degrees or undergraduate degrees in computing. This is a study that was discussed and presented about a year ago at a conference called Rebase by Professor Heather Miller from CMU. She really gives a very insightful talk and looks at a number of these statistics that have come out from US labor that sort of looked at how job openings are sort of in a tech-heavy world are growing, and where are those jobs going to be filled from? And if you look at the number of students graduating from colleges with CS degrees, the number of students who are taking coding bootcamp camps, and if you include all of that, you still can't fill the gap that's going to exist in a few years. Only 19% of jobs can be filled by US computing degree recipients. This is massive. There's a huge gap that has to be filled. And moreover, why this is important is because a lot of developers, 41%, according to a recent developer survey from Stack Overflow, more than 41% of developers have less than 5 years worth of coding experience. And if you look at the cloud today and what it takes to actually develop an application in the cloud, it is simply too complex. The clouds are very capable. They're very powerful. They allow you to essentially have supercomputing power at your fingertips, but they're massively complicated. But this is the reason why the cloud landscaping, the cloud computing landscape must change, because you have to make it more accessible to developers, and developers of various skill sets, not only the pros who can wield the power of the cloud, but also novice developers, people who are coming up and interested in sort of getting into cloud computing, or who simply have an idea and want to share it with the world. And one can argue that the cloud computing landscape has already changed. And it has changed and started changing 5 years ago with the introduction of serverless computing in the form of functions as a service, which I'm going to talk about. And the way we got to functions as a service is by looking at this evolution of computing that's been with us for decades. If you look at where we were with computing several decades ago, computing largely happened on-premise, on machines that you bought and you stored and you warehoused. And over time, we shifted to a model where you rented infrastructure. You rented machines from a cloud provider who specialized in creating warehouses for your data centers. And over time, abstraction also increased and automation also increased. And we ended up with things like platform as a service, Heroku, for example. This not only happened because of increasing automation, but because of shifting economics and incentives. So where you bought money, you spent money to buy machines in the past, now you spent money to rent machines per hour. So it also made it essentially more affordable. And functions as a service, which is one form of serverless computing, not all of serverless computing, but one form of it, takes that model to an extreme. Now you don't actually rent machines, but you pay per request. The totality of time that your function takes to execute is what you pay for. And so if your function isn't running, your code isn't running in the cloud, you pay nothing. So it's very attractive from an economic point of view, as well as the ability to essentially focus on just your code. So what is this functions as a service? It's really instantly reactive functions in the cloud. This is a very simple function in Node.js, receives no arguments and returns a result, hello world. And what I mean by instantly reactive functions is you can take this function and you deploy it to the cloud so that when an event comes in, like an HTTP request, but there could be many other kinds of events, the function runs on demand, consumes that event, produces the response, and then it's done. The resources that were provisioned to run this function are allocated on demand, and then they're dispensed with. And as I said, there's many kinds of events. It's not just HTTP requests, as a number of the demos I'll show here are, but you can have text messages, a tweet, an Instagram post, a file upload, an IoT sensor. You just keep on going. What really makes this model powerful is the event ecosystem you could put around functions to make them reactive and actionable. And so how do you get started with serverless functions? It's really two steps. You write a function and you're done. And you can try this out at a link that I've posted on this slide. And this is a function I've deployed ahead of time, just ahead of this talk. And what you'll see is you run this code is going to reply with hello stranger. If you open this URL and add a query parameter to the end, name and then your name, it will respond with your name. And you can see this and believe it for yourself. If you go to our functions playground, and Jamie should be sharing that link in the chat as I go, you can run your own functions and you'll have succeeded in running your first serverless function within seconds. What you'll see on our functions playground is a dashboard view that looks like this. In one panel, you have your code, and this is my hello world function that I just discussed. And then there's a run button. And if you click this run button, it will actually run your code. And moreover, if you click this publish button, you'll get a URL which is unique to you. And you can take this, and this is essentially your API that is now implemented by the function that you've created. And so congratulations, you've just run your first serverless function. And you've done this, and that function, if you share it with others, will instantly scale. As many events as come in, the cloud provider is provisioning resources and running that function as it needs to. And so in this case, all of your functions are running on a Nimbella cloud, and so the scaling is provided by Nimbella. And you notice that in the function that I showed you, It's just my function. I didn't write any server code. I didn't say set up a route. I didn't say listen to a port. It was just my function. And there was no infrastructure that I created. It was, again, just my function. You're going to learn more about this in the next 2 talks. And why is this so powerful? So I'm going to defer to that. But this is serverless. It's the ability to focus on just your code, the things that are essential to what you actually need to deliver your value to the end users. And by being able to focus, you can create faster. You can operate with less infrastructure because you're not worried about it anymore. It's somebody else's responsibility. With less operational burden because you're focused on understanding your code and observing what's happening with your code, not so much the underlying infrastructure and servers. So serverless comes about because you've punted essentially that entire responsibility and burden of managing the servers to somebody else. So I'm going to stop here and I'm going to transition to the next talk. So Srushith will introduce us to serverless. With this power comes a lot of responsibility and some constraints. So he's going to talk you through essentially some of these benefits and the rewards that you get out of it, and also some of the challenges that you see. Rob Allen will follow him to discuss some other aspects of serverless, also looking at the power of serverless functions. And just because they're functions and there's no servers doesn't mean you can't create APIs with them. And I think this is what you'll understand in the next 2 talks. Jamie, over to you.
All right, Rodric, thank you so much for that. Okay, so for our next presenter, we have Srushith R, who is the head of engineering at KonfHub. And for those of you that aren't familiar with KonfHub, KonfHub is actually one of the largest communities in India for hosting tech conferences. So if you are interested in hosting a tech conference in India, absolutely worth checking this out. And in this session, Srushith is going to be talking about Lambda and different aspects of it and mastering it. So Srushith, if you'll do me a favor, if you'll share your screen.
Can you see my screen?
All right. Yes, I can. And I will leave it to you.
Thank you so much, Jamie. Hello, everyone, and welcome to the first edition of this 3-hour serverless conference by Nimbella. I'm Srushith Repakula, head of engineering at KonfHub, and I'll be walking you through. This is the topic for my session: become Thanos of LambdaLand, wield all the infinity stones. So this talk is going to predominantly be about how you can leverage the power of Lambdas and build serverless applications on the AWS cloud. But this is pretty much on a generic level as well, and most of the concepts do apply for other cloud providers as well. A little bit of introduction about me. Thank you, Jamie, for the brief introduction. So I am the head of engineering at KonfHub, serverless consultant, and we also run, for people from India and from Bangalore, we also run the serverless architecture meetup group, which is in Bangalore, and I'm also a mentor at GirlScript. So there's a basic info about me. If you guys want to connect with me, have any questions, you can always reach out to me on Twitter or LinkedIn. And this is my Twitter ID. No. So, okay. For people who have already listened to me or know about me a little bit, they know that I'm pretty much into the cartoon world and the comics and things like that. And this talk is about how Thanos, the Mad Titan, wields all the infinity stones to basically leverage the power of serverless and bring back balance into life. So as Rodric had already mentioned, the evolution of serverless. On a very high level, this is how we have progressed as of now. We first, in the very beginning, had physical machines, and then we had virtualization, and then came in the cloud, where we had multiple cloud providers. Then the cloud was the boom, and then came in containers, where at each level, as you guys would have observed, there is abstraction at each level, and as Rodric had already mentioned, then came serverless into picture, where there is furthermore abstraction from the end developer, where a lot of things are taken away, and the only thing that a developer or someone who's building an application has to worry about is just writing their program and just writing the functional code, and everything else is taken care by the cloud provider. So this is a very brief introduction of what serverless is, if at all you guys are, if there's anybody who's getting started into serverless. Now, getting to the crux of the topic today, as if you are have watched the movie, the Avengers Endgame or the Infinity War, you will probably know about the 6 Infinity Stones. So today's talk is about correlating the 6 Infinity Stones of the Marvel Universe with what it could be in the serverless world. So here are the 6 Infinity Stones and what I think is the correlation between them. The Time Stone talks about the time characteristics, Power Stone is the memory, the Space Stone is about the code size, the Mind Stone, which is about the code itself, Reality Stone, the pragmatics about what serverless applications are and things like that, and the Soul Stone, that is the design principles. So these are the 6 topics that we will be covering today as a part of this session, and see how you can build and leverage the true power of serverless. Now, the first thing, that is the Space Stone, that is the code size. As I've already mentioned before starting of the session, this is predominantly, this is towards AWS and Lambda functions that I will be focusing on, but a lot of these topics are, do apply for other cloud providers like Azure Functions or Google Cloud Functions and things like that. Now, the most important thing, as I have just mentioned some time back, when writing or building serverless applications, is actually your code, right? So the functional aspects of what your application has to do is the only thing that you will be worried about or concerned about when you're building serverless applications. Now, writing serverless applications, like for example, writing a Lambda function is sort of similar to what you would write as a normal standalone Python functions or a Node application, but there are a few small minor differences which are very minute or not so significant, but they do play an important role in how your applications behave. One of the most important things that comes into picture is the code size. So when we are building applications, it is not just the code that we write, but it's also about the dependencies that we are going to consume or import or require as a part of our functional logic, right? Now, this dependencies that we import or require plays an important role because of the way how serverless applications or how your code runs in the cloud provider. For instance, how a Lambda function runs in the AWS cloud is basically you are provided. So I'll show you that. There's another slide on how that happens. So what happens is a particular virtual environment is created for you. Your code gets deployed onto that environment. And then based on, and all of this happens per event basis. So when there's a request coming in via HTTP trigger, or let's say some event trigger, like for example, an image is uploaded to S3, or there's some kind of an operation on top of a DynamoDB, or various n number of triggers that is available. So if there's any event like that, and then your Lambda function kicks in, and the cloud provider provides infrastructure for you where the code gets deployed and the code gets executed and the request is served. So this happens on the fly every single time there's a request that comes in. So there's no predefined or pre-warmed infrastructure provided for you. Not exactly, because there are a few offerings where a pre-warmed environment is available for you. We will get into that. But true serverless getting started, a Lambda function comes into picture only when there is a request that comes in as a form of any of the triggers. Now, why does the code size becomes significant or important as a part of a serverless applications? The reason is, as I have mentioned, as and when requests come in, the code gets deployed onto that particular virtual environment, and then the code gets executed. So the amount of time it takes for your code, your infrastructure to be provisioned, and as well as the amount of time it takes for the code to get deployed, and your dependencies also to get deployed into that particular virtual environment, is what we term as a cold start. Now, if we have really heavy packages wherein it takes a lot of time to deploy that particular dependency into the virtual environment that is created for us, then the cold start will be significant, and that will impact the performance and latency of our request. So if you, and as all of us know, it's really important for us to have very quick APIs so that the requests are fast and the end user doesn't have to bear that latency. Because of which the code size, especially the dependencies, become very important as a part of your serverless applications. We should try and avoid unnecessary code and dependencies that get imported into our application and keep that as small as possible. Now, this is a quick flow of as to how it works in the Azure cloud. So where the first one is when the app is cold, and the second flow chart is when the application is warm. This is pretty similar to with respect to AWS as well and the other clouds as well. We have the Azure allocates the unspecialized server, which means that the infrastructure is provisioned for your application. And then, as I mentioned, the code and the dependencies get deployed onto that particular server or that particular virtual environment, and then the function runs, the code runs. So this is what happens. The first half is when it's cold. The second half is when it's warm. That means there is a particular environment that is already created for you. The next request comes in. If the environment is already available for you to serve the request, it doesn't have to go through the complete cycle all the way again, but then just directly jumps into the last section that is running the code alone, because all of your code is already deployed and the dependencies are already deployed onto the particular environment, and all we need to do is we need to run the code. So that is what happens when a warm cycle, where only the code is run. So the time it takes from the first step till here is what we call as a cold start. And cold starts are one of it is something that is very much debated in the serverless world, where that is probably seen most of the times seen as a negative for a lot of enterprise applications and a lot of customers to get into the serverless world, where they believe that the cold starts are significant enough and the latency is very high. But as and when we progress through the talk, we will understand how we can overcome that latency, and also that a lot of the cloud providers have made a significant performance improvements and reducing that cold start to very minimal or at sometimes negligible enough. So that is about the code size. And coming to AWS world, we have something called as Lambda layers. So whenever we have large dependencies, what we could do is we could package them as layers, and it doesn't have to necessarily be large dependencies. A lot of times what happens is you have a utility library that you have written for your custom with some custom logic that connects to S3 or connects to a database and does some kind of a custom processing, and that utility library is consumed in multiple places. So instead of having it deployed as a part of every single function, we can add that as a part of a Lambda layer, and the layer can be added for every single Lambda function, and therefore the code gets, the code is available for all of the Lambda functions. Again, I've put this as a part of, just after we talked about cold starts. Now, one of the basic questions that a lot of people ask me is Lambda layers the solution for cold starts? Then the answer is absolutely no. It does not have any impact or anything on the cold start. It is just going to help us better deploy, better package, and faster deployments. Not the execution time, but it is just that it will help us with faster deployments. So what happens is every time you use a serverless framework or we have a CloudFormation template, what happens is the code gets deployed into an S3 bucket, and then that is used as a part of your Lambda function, right? So that can go down significantly. Your deployments can be faster because all of this utility code that is consumed by almost every of your Lambda function is already deployed onto AWS Cloud, and all you have to do is just import that layer. So this helps in reducing the code duplications as well, so that you have one central place where everything is available and you can just get the code from there, import or require the code from there. So this is nothing but essentially a zip file that generally happens when you upload to a Lambda function as well. This is very similar to that, just that this can be versioned, it can be shared as well across Lambda functions and outside of Lambda functions as well, where you can share it with other people, and you can easily import into your Lambda configuration. And as of today, we can have up to 5 Lambda layers as a part of one single Lambda function, where you can add multiple layers and things like that. And for Python, for folks who use Python, if I'm not wrong, AWS by default provides a layer for NumPy, wherein you don't have to provision, you don't have to maintain that layer, or probably you don't have to publish that layer, but AWS takes care, and you can directly import it in case you're trying to do some kind of NumPy related stuff. Now, the next one is the milestone, which is the code itself. As I have mentioned, the most important piece of your serverless architecture is your code, because essentially that's the only thing that you're worried about, or that's the only thing that you write. Right? You don't configure anything else. Now, most of the times what happens is in serverless world, a lot of times we migrate the application from what we have already built into the serverless world. As I've mentioned, it is not very different as to what you write in the normal world versus when you migrate it to the serverless applications. But one of the most common things or mistakes that most people make is they just migrate that entire monolith from their existing architecture into the serverless mode. So what happens is there are multiple triggers that is available, and there's one single fat Lambda function or Azure function that takes care of all of the processing. Now, this is sort of an anti-pattern, because the whole point of serverless is to make sure that it is sort of a nano service, if you can think about it, right? Where each of the functionality is broken down into its own individual Lambda functions, and that particular Lambda function takes care of one and single only thing. That is what we call as the single responsibility principle, where one Lambda function has the code that is required to do only one specific functionality. Now, what you would rather do instead of having a one big fat Lambda function is you break it down into multiple Lambda services that is essentially translated into multiple Lambda functions, and you could probably have a lot of event triggers, and then they could internally communicate with each other using a lot of other services. You can call one Lambda function to another, or there's some asynchronous processing that is possible. Or if you want to really orchestrate multiple Lambda functions, then we have step functions as well in the AWS world, or logic apps in the Azure world, where you can say that after execution of this Lambda function, the next is this, the next is this. Then you can do a lot of other out-of-the-box logic, such as you probably can do parallel processing of Lambda functions, do some decision-making things at the step function itself, which says that, okay, if the response of my Lambda function 1 is this, then execute 2, otherwise execute 3, and things like that. So we will touch a little bit upon what step functions are and how it is can be consumed in the serverless world in some time. Now, there are a few code patterns as well when we move to the serverless world, which is the microservices pattern, where each of your microservice becomes a separate Lambda function. The other one is the services pattern itself, where a particular service becomes a Lambda function. To give you an example, let's say you have a social networking site which you're building. Then you can have the users module. The CRUD operations on top of the users can be one particular Lambda functions, that is the get, update, delete, and list APIs can all become one particular Lambda function. And you can do what you can do is you can have multiple endpoints for the same Lambda function with multiple methods, and you can sort of do a minor routing sort of a thing in the Lambda function to probably trigger the specific code that is required based on the input that comes in. So we can easily inspect the request that is coming in, understand what is the type and probably a few more request parameters, and decide on what sort of functionality, what piece of code that needs to be triggered. This is one of the things that we can do with the services pattern. The microservices is much more granular in piece, where you can probably have a create user as a one Lambda function, update user as a Lambda function, and things like that. The problem with the microservices pattern is that the more you split it down, as I said, it's more towards a single responsibility principle, right? Where each and every Lambda function does only what it's dedicated for. But the problem is, as and when your application grows, it becomes big and you have a lot of functionality that is getting added, the number of Lambda functions also increases. And after a point of time, you have so many Lambda functions that is lying around, it sort of becomes unmaintainable sometimes. So a lot of people prefer the services pattern where they modularize their code and put one particular module and then have like 4 APIs. Like I said, the CRUD operations and all of those 4 APIs talk to one Lambda function, and inside the Lambda function, there is a routing, a simple routing mechanism. You can probably use an if-else ladder if that's okay. And you can simply route to the particular logic that is required to perform based on the request that is coming in. The monolith pattern is something that I've already mentioned. You have one big fat Lambda function. There's one single any method API, and we have a proxy API where every request that is a part of our application comes into one particular Lambda function. And internally, you have a complex routing mechanism where you understand based on the request that is coming in, you route to different functions of code. That is the monolith. The other is the graph pattern, which is more towards the GraphQL style of doing it, where you have one or two endpoints, but then you have an app sync as a service, and where it routes to specific Lambda functions, and that takes care of the routing for you. So these are the various code patterns that we can follow as a part of building your serverless applications. And as I've mentioned, when you build serverless applications, you're breaking down big monolith applications into smaller nano microservices. And with that, it becomes really important for us to orchestrate the flow. If at all, you are dependent after execution of Lambda 1, you have to execute Lambda 2 and then Lambda 3 and things like that. So a situation like this will most likely occur. This is where you maintain a state. And I think there is a talk later in this event where it will talk about stateful applications. From the AWS world, we have the step functions, which takes care of where you can write simple JSON code, and it takes care of orchestrating different Lambda functions. And in the Azure world, we have something called as logic apps. And you can also use message queues, where you have an SQS, or you probably can have an event bridge as well, where you push some messages, and there are dedicated Lambda functions that take care of reading from the queue and executing their own things. So this is more from an asynchronous way of doing it, of how you can orchestrate your code. The other way of doing is obviously you can call one function from another function, if at all they are segregated into different Lambda functions, and get the work done. That can be synchronous as well. It depends on how you want to execute your code. Then, because we have already touched upon the code size and how it impacts the execution of your functions, Lambda functions. Here's a small snippet from Yan Tsui, another AWS serverless hero, where he talks about the cold starts and how it impacts the performance of your Lambda functions. This is quite some time back. Obviously, there has been a lot of improvements and enhancement that is done. I have already also put up the link to his article here, where he talks about how heavy the AWS SDK itself is and how it impacts the cold start as a part of your execution. The one that you see here is actually a snippet from a service called as AWS X-Ray, which takes care of monitoring. It's a monitoring tool, monitoring service on AWS, which logs data at every single data point. And this is just an article that talks about how heavy the AWS SDK that you see here. This is the initialized container Node.js runtime. This is how long it took for initializing the environment, and then this is the amount of time it actually took for the code to run. This was just a simple hello world program, and as you can see, the code and the dependencies play a significant role as to how your performance and how your response times are. The next characteristic, or the infinity stone, is the time stone, which is the time itself. One of the two configurable things as a part of your Lambda function in the AWS world is how long can, at max, your Lambda function run. So what we can do is, again, the billing is also dependent on how long, because in the serverless world, it's always pay as you go. So you only pay for how long you have your code executes, right? And therefore, if you think about it, all of these things come together. Your build as to how long your code runs, and this includes the cold start as well, right? and not so now in the latest in the last few months. It's not the same case with AWS, but you're built according to how long your code runs, and therefore it becomes very important you understand how your code behaves, and also it is very important you choose the particular runtime in such a way, right? Especially Node.js, Python, and these kinds of runtimes have been very much suited in the serverless world, where it's very quick to run your functions and there's not a lot of latency when compared to what Java could be. So here is a simple snippet again, where this is a simple Lambda function that calculates 1,000 times all the prime numbers that is less than this number. And as I've mentioned, there are two characteristics that is configurable as a part of your Lambda function. One is the RAM and the other is the time limit. Now the RAM. So this on the left-hand side is what you configure the RAM for. That is, RAM is nothing but the memory. It's not essentially the RAM of your Lambda function. It's just the memory. So you configure the memory, and AWS allocates an equivalent amount of compute power for your Lambda function. And as you can see, based on how powerful machine or how powerful the infrastructure is, let's say for this particular Lambda function code, it's a 128 MB Lambda function. It took 11 seconds, and it's costing around $0.024 dollars. Right, and as and when we increase the memory that we are allocating for that particular Lambda function, the response times have significantly come down. And as you can also observe, that the pricing is not changing a lot. From a 128 MB to 1 GB memory allocation, there's not a lot of difference at all. Or probably it's in the fifth decimal, right? Which doesn't really matter, but you can see the response times have come down to almost 10% of what it was. So especially when you're building serverless applications on the AWS world, it is really, really important for you to understand what is the best RAM configuration or memory configuration for your Lambda function to get the best out of your Lambda functions. So touching about a little bit of how the code works, so the code starts is as a part of Lambda functions. There's something called as global variables. And the global variables in the AWS world, this is very essential for people who are getting started to understand, because when I was starting, this was a weird behavior for me. What happens is everything that is at the global level is cached for subsequent executions. So this is a simple example where I have a connection to my MySQL database, and I have kept it at the global level, and then this is my handler code, which is executed. Whatever you see here, the second part that is a blue in color is executed as a part of every single execution. But then what you see on the top, that is the yellow in part, is executed once every warm state. So cold state. So whenever the virtual environment is provided for you, that is when your code gets deployed. That is when whatever is available at the global level is getting initialized for you. The global variables are initialized at the time of initialization of your environment. So you probably have to be very careful as to what variables you're assigning at the global level. And if something is fishy about, something is not getting updated properly when a variable is at the global level, then you probably have to see it probably is because this is executed once every time the environment is provisioned for you. Now, that is the sad part of it. That is the flip side of it. What is the advantage? So here what is happening is I'm trying to maintain a connection to my database at the global level to understand, to ensure that I don't have to connect it for every single request that is coming in, but I try to reuse a connection that is probably available as a part of my previous execution. Again, this is against the practice because Lambda functions or serverless applications are meant to be stateless. But here we are trying to maintain or trying to utilize something that is from the previous state. This is something against what it has to be. But again, if you want to leverage, you want to reduce that latency just a little bit, then this is sort of a hack that you can probably look at. And the next is the memory, the power stone, which we already discussed. And when you increase your RAM, you can reduce your costs and the performance can obviously increase. And this is one particular open source tool, that is the AWS Lambda Power tuning results, where I have just added this link here. What it does is it runs your code across different RAM configurations and tries to understand which is the best suited configuration for your function. And it just gives some beautiful results like this, a beautiful graph, which you can probably, you can take, if performance is the most important thing, then you can probably look at, the maximum RAM that is available, or then if cost is the most important, then you can probably reduce the RAM. You can probably take a middle ground, try and play around with the different configurations to bring out the best of your Lambda functions. The next one is the design principles. As I said, a lot of times what happens is when you are moving to the serverless world, it's not that all of the services that you're trying to consume is a part of is all serverless. Let's say, for example, you have a relational database that is not, and as most of you might probably know, Lambda functions or any serverless functions can scale automatically, automagically, without any configuration, right? You don't have to configure for anything. You just say that this is my configuration, this is my code, and the cloud provider takes care of automatically scaling based on the number of requests that is coming in. Now, your serverless function can probably scale, but that doesn't mean the downstream services that the Lambda function is consuming, or Azure function is consuming, can automatically scale, right? Let's say, for example, in the AWS world, you have a relational database, that is the RDS, that has a limitation on the number of connections that can happen to a particular database at a given point in time. So your Lambda function can scale, but your database cannot. This means that even though you're building a serverless application, you're tied down to the constraints of your database, but you want to leverage the true power of serverless. How do you take care of that? You probably change your architecture a little bit, where instead of directly connecting to your database, you try to poll, you try to, if at all, it doesn't have to be real time, you probably push it into a queue, and then the Lambda function can take care of picking the request from the queue and then writing into a particular database. That is one way where you don't want to migrate the database also into a serverless offering. Or rather, if you're okay, and there are a lot of serverless offerings of the database itself, especially on the AWS cloud. You have DynamoDB, the NoSQL way. If at all that's not, if it's a NoSQL, right? You have already built your application with a SQL. Now you're shifting over to NoSQL, then it's probably not possible for you to rewrite your entire application. Then things like this probably can help you, where your downstream database constraints are not pulling down the capabilities of your Lambda functions. That is one way. The other way is, you can always have, you can set a limit on the number of requests, the number of concurrent requests that can happen in your Lambda function, and therefore, you only accept those many requests. But that is, again, you are sort of moving away from the beauty of serverless, which is basically scaling how much ever you want without any configuration. So whenever you move into the serverless world, the important piece is to remember that it's not just about your Lambda function or your Azure functions or cloud functions or whatever it is, right? It is about the entire application itself. The serverless, the Lambda functions or the Azure functions can scale beautifully, but it doesn't mean all the other connected services can probably. So you have to keep that in mind as a part of your designing, as a part of your architecture. Now, this is something what is a step function would look like. And as a part of your serverless architecture, it is very important for us to design for failures and duplicates, because we can get a lot of requests that is coming in at a single point in time. So you just have to configure. So this is multiple steps in my step function. So basically, I'm maintaining a sort of a state. And then what happens is I can configure failure. So if this fails, then go here. If this fails, go here. Then parallel processing and things like that. So this is what you can handle as a part of your step functions. The next one is the reality stone, that is a pragmatics. A reality is merely an illusion, right? Albeit a very persistent one. So what we see out of the documentation or what we see out of the offerings will most likely not be the same thing when you start building your applications, right? as I have mentioned, serverless is easy to code, easy to get started, but really hard to design for scale. I mean, a scale in what I mean is different applications that come together and play as play together to bring out some beautiful music. So it's really important for you to consider the concurrency that we talked about, and then the latency caused by VPC. This is again specific to AWS, but then there's a lot of improvements that has come up where Lambda functions inside of VPC had a terrible cold starts, but now the significant improvement, so that is no longer a road blocker, and the database constraints is something that we have already talked about. And then the cold start thing, a lot of people, what they do is they trigger some CloudWatch, they trigger some schedulers that keep your functions warm all the time to ensure that it's a warm request every single time. But then there are a lot of other other offerings as well. Let's say, for example, in the Azure world, where you have a dedicated plan where you can say that this is the pre-warmed environment for me, and my Azure functions should run on top of that, so that the warm start is taken out of it. In the AWS world, you have something called as concurrent executions, where you can specify that these many Lambda functions have to be pre-warmed for me all the time, so that these requests, the first set of requests that come in, don't have to go through this cold cycle and then directly onto the warm. A few things, the last thing that I would like to put up is a few things that you have to keep in mind is the single responsibility principle, which we talked about as a part of our code patterns. You can probably, that's a best practice, but you probably would eventually like to break it, because having one Lambda function that does just create user is a little too much to maintain, if you personally ask me. And then state management is against the design, because serverless applications are meant to be stateless, but then you eventually maintain states, as I've mentioned, the step functions and multiple other ways. I think there's another, as I've mentioned, there's another talk as to how that happens. And then always keep in mind that you design your application with serverless in mind. It's not the Lambda function or Azure functions, but it's the entire application that has to be taken care, not just one particular service. So keep that in mind when you're building serverless applications. Well, that is pretty much about with my talk. So if you guys are interested of connecting over me to talk about serverless, anything about serverless, you can reach out to me in different places. There's my Twitter ID, GitHub, and LinkedIn as well.
All right. Hey, that was a fantastic presentation. Great way to start off 3 hours of serverless. Thank you so much for doing that.
Thank you, Jamie.
Cool. And I think we have enough time for maybe like one or two questions. So you actually got a lot of questions in the chat. I'll go ahead and bring up the first one, and I hope I'm gonna. So one of the questions you got: can we consider Saga pattern as one of these serverless code patterns?
Sorry, can you just repeat that?
Can we consider? I believe it says, can we consider Saga patterns as one of these serverless code patterns?
Oh, okay. I'm not really sure about that pattern. I'm really sorry about that. So I really can't answer that question.
Okay, that's fine. Well, I thank Cloud Computing for asking that question. Another question you got. So why is serverless a good thing?
Sorry, what is serverless a good thing? Why?
Yeah. Why is serverless a good thing in your opinion?
Okay. I mean, I have actually started my entire development all the way from serverless. So one of the best thing about us building serverless applications, if you ask me, is one is the time to go to market. It's really quick for you to build up a POC or an MVP for that matter, and just go to market, just build some very basic functionality and go to market, evaluate what your product is and how the market is accepting it, and then come back and make more enhancements and improvements to it. I think with serverless, the deployment cycle, the development cycle, is very quick, where you can easily spin up APIs and write some basic code, like Rodric had mentioned, right? A simple hello world application probably takes less than 2 minutes to do. And if you want to build up some simple applications, it's not going to take a lot of time, and it's very easy to get started. That is the very first beauty, if you ask me, about building serverless applications, where it's very easy to get started and get something up and running very quick, so that you can evaluate your idea, you can evaluate your POC, and things like that. That's the first thing. The second thing is the scaling and the maintenance that is taken out of your hands. As an individual developer, you don't have to take care of anything. All you have to take care of is you're writing your own code, just solving the real world application problems, and then you're done. The third thing is the scaling and performance that is coming out of the box for you, that you don't have to auto scale. I mean, you don't have to configure anything, right? It scales automatically. The fourth thing is the costing, because you pay as you go. You don't pay when you are not executing anything. I think these are the four essentials that drives me to build any application into the serverless world. Especially the cost is something that a lot of people really look at, and the time to go to market. So these are the two really great things about building serverless applications.
All right. Hey, that was a fantastic answer. So I guess, so we're going to go ahead and wrap up with your session. Thank you so much for that. All right.
Thank you so much.
All right. So now we're going to go move on to the next person. All right, and you have a good rest of the night. Oops. All right. Okay. So for our next presenter, we have Rob Allen. For those of you who aren't familiar with Rob Allen, he is a software consultant who has contributed to a ton of open source projects online. And in this session, he will be discussing PHP in a serverless world. So if you program in PHP and you want to step your game up with serverless technology, I would strongly recommend sticking around for the next 30 minutes. Rob, how you doing?
Hey, Jamie, I'm doing very well, thanks. Well, I say very well. Clearly, I'm from England, so I feel like I should talk about the weather, because that's what we do over here. And the storm is coming in. We have Storm Francis about to hit around this way. It's been very windy all day. It's been pouring rain. So I'm doing okay, but outside is not so good at the moment.
Yeah, you should come to California. Our weather is good here every day. Just
Yeah, I've heard that, but it's an awful long way away.
Yeah. Well, okay, so I guess we'll go ahead and get started with your presentation. If you'll go ahead and share your screen, we'll go ahead and get you started. All right. All right, floor is all yours.
Excellent, thanks. Okay, hi all. Where do I want to start? Obviously, I've been expertly introduced there by Jamie. And the only thing I think he missed out was I'm heavily into APIs. I'm an independent consultant. I do development for clients in a variety of industries, mostly enterprisey, mostly banking or finance or healthcare, things like that. So I do quite a lot of API type work, and that's kind of how I got interested in serverless in the first place. So I think it's quite good for that. As you can tell from this particular slide title, I'm into PHP. I think PHP is a very good language for programming the web, and it is still current, and it is worth using in the serverless world. So we're going to talk about that today. So let's get started. Lessons of serverless number 1. You will have no choice but to use JavaScript. This is nonsense. However, you'll spot that the first 2 talks today both showed JavaScript and not other languages. Though admittedly, the last one did mention Python as well. There are plenty of languages you can use for serverless. Here is a selection. You've probably recognized most of those: .NET Core, Ruby, Java, Python, obviously, and obviously JavaScript, and also PHP. So PHP is the one that I want to talk about today. And although I'm going to be talking about it, I do encourage you to look at the alternative languages. They might make more sense for your situation, for what you're doing, for your comfort level. There's a lot of new tech in serverless world, so you may want to not introduce a brand new language at the same time. So pick the language that makes the most sense to you. Obviously, I'm talking about PHP. So you can imagine what the first question is. Why? Why PHP? What on earth are you doing using PHP? Let alone what you're doing using PHP in 2020 in serverless. Well, hopefully I can explain a little bit about that. So PHP fits remarkably well with the serverless paradigm. So the key things that I think that work really well with PHP and serverless are our development mechanism, paradigm rather, of statelessness. PHP developers have been storing state externally since the beginning. That's how we always do it. The shared nothing architecture of PHP is a natural fit for serverless. It works really, really well for horizontally scaling. That's why PHP applications are relatively easy to scale horizontally because of our shared nothing architecture. And serverless works on a shared nothing architecture. Wonderful. We already have a leg up in understanding A, how serverless works, and B, natural fit for the way we think. PHP is also a synchronous language, as are other languages, but JavaScript is a bit heavier on the asynchronous mechanisms due to the way Node works in terms of serving websites via Node.js. You tend to see a lot more asynchronous stuff happening there. And serverless functions, not so asynchronous. If you need asynchronicity in serverless, you should be fanning out to separate functions. You should be putting in message queues. You should be letting the provider and the system handle that for you. So each individual function is more likely to be single task, single threaded. And PHP and other languages along those lines are particularly good at that. So I think that is quite an interesting thing as well. I think I should also mention that we're up to PHP 7. This is not the PHP you remember. PHP 4, PHP 5, we are no longer back in 2004, 2010. We have a mature object model. We have competent package management in Composer. We have type declarations. We have good error handling. Language errors are now caught as exceptions. Good exception handling in general. Internally, the runtime has an internal abstract syntax tree. This is not the same PHP as what you might remember if you haven't touched it for a decade or something like that. There's mature development practices. We have design patterns, we do unit testing, static analysis tools. All those sorts of things are now done in modern PHP development in 2020. And it's an awful lot faster and much more memory efficient nowadays than maybe it used to be. So what do I mean by faster? Longer is better in this graph. Back in the PHP 5.6 days, this is WordPress, we were getting on this particular benchmark around 200-ish requests per second. No code changes, no server changes, just change the PHP runtime to PHP 7.2, and we've more than doubled our performance. That's how much faster PHP 7 is. And PHP 8 is just around the corner. It's going to come out this year when we get a JIT as well, which may or may not make a difference for a lot of real world scenarios, but focus on performance is still continuing in the PHP world. Lower memory. In this one, smaller is better. So back in the PHP 5.6 days, standard request, you're looking at 100 megabytes of memory. PHP 7, no other changes, 15 megabytes worth of memory. Significant memory improvement. And one of the things that affects the pricing and performance of your serverless functions are speed and memory. It's how you're charged. So these are good things. PHP is quite a good fit for serverless. Serverless platforms. Here's a few serverless platforms. There are many more serverless platforms than these, but I've selected a few here to provide some idea of the breadth and available. So you've got sort of the big ones. AWS is obviously a huge one. Azure, the Google people, they do serverless. IBM, Cloudflare, a bit more niche. Nimbella, same thing. And then down the bottom, we have some open source providers. So you've got Function, FN, OpenFaz, which is really quite popular, and Apache OpenWhisk, also popular. Also all serverless platforms. You can pick your choice. They'll work basically the same way. What about PHP? How does PHP support fit? Something like this. So PHP is not that niche. It's on an awful lot of the platforms. Not on Azure yet, not on Cloudflare Workers, Google Cloud, it's got that dotted line because they're still in beta for their PHP support. But you can do PHP on AWS, you can do it on IBM Cloud, you can do it on Nimbella, you can do it on Function, you can do it on OpenFaz, you can do it on OpenWhisk. You can do it quite a lot of places. It's pretty easy to get started. Now, I said they're all basically the same, so let's look at some code. Here we go. Hello world. Traditional hello world. This is what it looks like in AWS Lambda if you use Bref. So it's just a function, takes an event, returns a string. If you were listening to Rodric's talk right at the beginning, pretty much identical to the way the JavaScript one works. This is the one in OpenWhisk. Pretty much the same thing. Here's the one in OpenFaz. Oh, we've got a class this time, but it's pretty much the same thing. We have a function that returns a thing. Here it is in Google Cloud Functions. Guess what? It's pretty much the same thing. Doesn't really matter what your provider is. And here's a secret. You're going to hear a lot about lock-in and serverless. The lock-in is not with your code. It's with the surrounding stuff of your application. Moving your code to another provider is never the problem. Now, I'm quite into technology. I'm very, very into open source. As Jamie mentioned at the beginning, I've contributed to open source projects. I like open source. I think it's a net good for the technology industry. So we're going to talk about an open source thing here today, Apache OpenWhisk. Now, I do have to admit some bias. I'm a contributor to Apache OpenWhisk. I contribute to a lot of programs, but I'm also a contributor to Apache OpenWhisk. I wrote the PHP runtime for it, so I know it remarkably well, but there is a bias there. So hold my hands up, be honest about this. It's fantastic, if I do say so myself. I like it a lot. I think it works really, really well. It's used in a remarkable number of different places. IBM use it as the underlying for their cloud function system. Nimbella use it as the underlying thing for them. A major Korean provider also use it as the underlying system for their offering. And it's used in a load of different places that we can't necessarily talk about because of NDAs and private enterprise and things like that. It's good. And it's Apache. What can you not like? So let's go back to that function and talk about how it works. A little bit at least. We have our entry point. It's called main in Apache OpenWhisk because main is a traditional function name for the entry point to your function. Goes all the way back to the late 60s, something like that, with the C programming language, possibly even the B programming language. That long ago, always had a function main. Everything related to this particular event comes into your event parameters, comes into your function. So that's a quite nice bit of isolation there. Everything you're interested in is passed into your function for you. And then we're going to do some work. Firstly, we need to handle our input. Just like any other programming and the sort of program we're going to do, you're going to have to deal with your inputs, going to do something with them. Then you're going to do your actual real work. This is your business logic. In a hello world application, your business logic is remarkably simple. All we did is concatenating $name to hello. And finally, you deal with your result. You deal with your presentation logic. And again, in serverless world, it's remarkably simple. We just send back a associative array. And that all works really well. I can call that from a command line. I can call that from a scheduled task. I can trigger it from a database change or something like that, all very, very easily. But I'm to API. How do I do it with APIs? To trigger my function from API, I use an API gateway. My API gateway is going to provide things like routing, or if you're an American, you might say routing. I'm sorry. Rate limiting, authentication, custom domains, all that is the province of your API gateway. And once it's done all that, it will then trigger your code that runs in your serverless function. So your basic pattern looks something like that. Got your HTTP client, API gateway, your serverless function. Set everything up, we use the command line. So WSK is the command line tool for communicating with the OpenWhisk system. Create an API. It will tell me it's happy with that, and then I can call it. I'm a really big fan of curl. If you're going to do any API work, I highly recommend you learn curl, but you should probably also learn Postman or POR or Insomnia or one of the GUI clients as well. But having a good understanding and use of a HTTP client will make your life much, much easier. And of course, we get our message back. Hello, Rob. Excellent. So let's talk about HTTP APIs. Just because it's serverless, we can't ignore the basics of writing a good application. I know all the serverless stuff is new and shiny, but we are still writing professional applications that are being used by clients, by client developers. We need to make sure we get it right for them. We need to have status codes, method negotiation, content type handling, error handling. Get your error handling right in an API. By far my biggest bugbear. It's so hard to deal with an API that doesn't do good error handling. Get it right. Media type formats, all the other things about an API you need to get right. Status codes. There are only 5 groups. All the numbers are 3 digits. The first digit is the group, 1, 2, 3, 4, 5. And the second 2 digits are the actual number. And the groups mean something. So a 2 series or a 200 series is a successful message, a successful response. A 400 or a 500 type message is an error message. Going back to error handling, if you have an error situation, make sure you do not set the status code to 200 because it's wrong. Bad things happen all across the network. Do not do that. Use a 4xx or 5xx code and your network will thank you for that. For that, you need full control over the response because by default, nearly all the serverless providers will send back 200 for our API gateway unless you tell them otherwise. In OpenWhisk, you do it like this. We send back a return associative array with 3 actual keys, status code, headers, and body, and we have full control. In something like AWS Lambda, you send back a PSR 7 response object, and it will do the same thing. Full control is really, really important. Get your verbs right. Same reasoning. There's something called idempotency. You must get and understand the importance of verbs for making a great API. Because it's serverless, still get this right. If you can make your idempotent, will be much better. So what do I mean by idempotent? By idempotent, I mean if the client repeats a successful action, they will get the same result. So get is obviously idempotent. I can retrieve something again and again and again, and it will just work. Get the same result every single time. Delete is obviously idempotent. I send a message to delete an item. I can send that message as often as I like. The net result is that item is still deleted. It doesn't magically come back or something. Post is not idempotent. So when you send a post request twice, you're likely to get 2 different records at the other end. If you use a put request, that will not happen because put is idempotent. Makes a difference. Makes your API easier to reason about if you can use idempotent verbs. What about that request information? Getting all that data. So we've got on the OpenWhisk side, the actual parameters from the query string or from the post body or the put body or wherever they've come from are straight keys in our args array. So they're dead easy to get at. There's also some magic __OW prefix keys for the actual nitty-gritty details. And again, Lambda or Google Cloud Functions or FN all have their own mechanism, which is basically very, very similar to get at this information. You can get at the method, you can get at the path, you can get at the headers, etc., which can be quite helpful. So basically, I want you to be aware that if you're writing serverless, you are still building an application. And I'm interested in APIs, so I'm going to tell you about APIs and why I think it's important to get this stuff right. Okay, let's look at a case study. Now, most of the work I do is obviously, I suppose, under NDA. I'm a consultant. I can't just go showing you client code because my clients would get very upset with me and I was unlikely to get more work from them. So we're going to look at a serverless API for To-Do Backend. To-Do Backend is a sister project of To-Do MVC. To-Do MVC came first, but between the pair of them, they make a task manager, a to-do list type application. To-Do MVC is for JavaScript front-end applications that implement adding an item, setting its complete or changing its order, marking it done, etc., stuff like that. There are an awful lot of JavaScript frameworks. Wow. I don't front-end at all. It's MVC, I had a look and went, wow, that's an awful lot. And To-Do Backend is the API half of a task manager application. So the front end will communicate with the back end. So you need to be able to create API calls to create a task, delete a task, list tasks, etc. And To-Do Backend showcases all the different ways you could write the standardized API in different languages and frameworks, like in Node using Couch or in C# using SQL Server or whatever. So it's quite a good way to compare different frameworks together. So this is what our architecture looks like. We have our client, we have an API gateway, we have multiple serverless actions, and we have a Postgres SQL database, because that's the one I picked. Elephant SQL, by the way, is the provider I use. My serverless functions do one thing and one thing only. So I have a separate function for each operation that the API can handle, and the API gateway handles the routing via the URL path and via the method to ensure the right function runs. So now I've got multiple functions in play. I probably don't want to have to handle uploading them all, setting them all up using that command line. It's great for one-offs. It's not so great for an application you want to reliably deploy. So how do we do that? We do that using deployment tooling. I'm going to use one called Serverless Framework, but you could equally use CloudFormation, for instance, from AWS, or Terraform or something like that. It doesn't really matter, but investigate and learn a deployment tooling system. It's known as infrastructure as code. And the best thing about it is you describe your application as a configuration file. In the Serverless Framework, it's called serverless.yaml. And you can put that in VCS. You can put it in Git. And once it's in Git, you can diff it. You can see the changes. You can reliably deploy. Can't recommend this enough. Big fan of reliability, big fan of version control systems. So in this particular one, we set up the service and stuff like that, and then we need to configure our action. So I have a function section. We're going to look at one action today, the edit to do action. I have a handler, so it's going to be edit-to-do.php, the main function, as we've covered before, and I give it a name, edit-to-do. And I give it my events. So my events are how will I trigger this function. And this particular one, it's going to be API, so HTTP event. Give it a path. It's going to be a patch message to /todos/ID. So I can figure that up, and the API gateway will do the right thing. So that's project files. So this is a standard PHP project. It looks like any other PHP project. So we have a source folder, we have a vendor folder because we're using packages, we use a composer, which is why we've got composer.json, and of course my serverless.yaml file. My source directory looks something like this. How you organize it is up to you. But for me, I put all my application core code separately. I put it in the to-do namespace because it's not dependent upon being in serverless. I could move this entire application to Laravel and all the to-do stuff would stay the same. I would just need to change the front-endy bit, the coupling with my framework, and that's in the actions folder. So my actions folder has a separate PHP file for each serverless function. And that's where I do my separation of concerns. Just sensible and standard engineering and development of a project. Just because we're in serverless doesn't mean we throw away all the knowledge we've already got. edit2.php looks something like that. Now, I appreciate that we're online, and so I'm not on the stage and it's right back behind me, but you've got to get really close to the screen to see that. So let's look at it in a bit bigger, in bits, in chunks. So firstly, we have our error handling. I mentioned before, error handling is really important to me, particularly getting the status code right. So for every single function I write, the first thing I do is put in a try-catch statement, catch on a throwable, so I will pick up any errors that occur, and then I can handle the errors the way I want to handle them. And I can try do my work. So it's a pattern I use. I think it works remarkably well. So what do we do for error handling? First off, write the error log. We're going to have to work out why the errors occurred at some point. So writing to the logs is really, really helpful. In general, in the serverless environments, getting logs is usually aggregated somewhere, so you can go and find them relatively easily. Consider adding a request ID or trigger ID or something like that to all the logs that happen on the same message or for the same event. Because particularly if you've got multiple actions in play, being able to trace through the multiple actions or the logs of the multiple actions becomes quite useful. So consider doing that if you need it. Set your status code. Not particularly complicated, this code, but if I get a code that's less than 400, I'm going to set it to 500 because it's an internal server issue. And then I can return to the client. So I can set my status code correctly, and I can return a body with the message from the exception. So we get an error message. Depending on your particular application, you may want to do more complicated error handling display, error rendering, in which case look at RFC 7807. That's not a bad idea for looking at how these works. Onto the meat, onto the actual function itself. What does it look like? As with every other application, we're going to deal with our input. We're going to read our input. First thing we need is the ID from the path parameters. What do we do with any piece of information that comes from the client? We do not trust it. We never, ever trust it. In this case, I validate by casting it to an int. For other applications, you may wish to do more validation than that. But again, just because it's serverless doesn't mean that we forget everything we already know. Always validate your inputs. Same thing with our body. Here I'm JSON decoding the posted body, or the body that came through the patch request. If it fails, then I can detect that, and my domain logic is going to validate it. Don't trust user data ever. Standard part of our code. Now we're going to do the real work. Because my domain logic is completely independent of my action, I just have a mapper class that can load the to-do record up, and it can update the to-do record. And the load by ID, sorry, the update rather, will do my validation in this particular case. I don't need to show you that code. It's particularly boring. If you care about it, it's on GitHub. But practically, you're going to put your domain logic, your business logic, the code that does the work, somewhere else. Resources, present your resources, send them back out. Don't couple your database to the user. Sorry, don't couple your database to the domain. So what I mean there is that what you send down the wire should not be a direct representation of what's in your database or in your persistence layer. Separate the two. The way I do that in PHP is a component called Fractal, which will generate me an output in one of the variety of serialization formats that are acceptable, like JSON schema or HAL or something like that. I don't particularly care what you use, but you will thank yourself later if you can change the database record without screwing up your JSON output. Deployment. We're using the serverless framework. So here's our deployment. We run serverless deploy from the command line, and it goes away and does all the work. So I'm running it from the command line here, but you can put this into your CI tooling. So I could quite easily make it such that when I create a new tag and I push that tag to Git, my CI tooling kicks in. It can run the tests. Once the tests pass, it can then do a deploy for me. We can start doing some interesting things once we've got infrastructure as a service in place, which I highly recommend, as I've said. And we end up with the working API. I picked the vanilla JavaScript example for my front end, but you can practically use one of the many different examples I've got to do MVC that all talk to my API because it's a standardized API. I've completely decoupled my front end application from my back end, which is also quite a useful thing to have done. And obviously, because I'm English, my only to-do items are to drink tea and eat biscuits. So thank you very much. I hope you found that useful. What I want you to take away from this talk is that serverless is an important technology for the future. It is going to become more and more prevalent, if only because the value proposition is so good. And that's letting and putting aside how quick it is to get started. So we'll see more and more serverless happening. Just because you're using serverless does not mean that you can forget anything about good software engineering. You still need to do that. And you don't have to use JavaScript. You can use PHP. PHP fits really, really well. And PHP 8 is coming later this year. Thanks very much.
All right, Rob, that was fantastic. Thank you so much for giving that presentation.
You're welcome.
So, by the way, I love the inclusion of tea. As someone who drinks probably 3 cups a day, I could definitely use that.
Well, it's certainly our national drink.
Yes. So you actually did get a few questions. So I think we have enough time for like 2 questions. So one of the questions you got, can the projects on To-Do backend website be used for some personal hands-on? I didn't see any license info.
Well, it all depends on all the ones that are put up there, but I'm pretty sure that one of the requirements for submitting to the project is that you have a compatible open source license. So I've certainly used it for looking at how to, because the problem space is consistent. You can look at various different applications, implementations of the same application. So I've looked at how it's done in Laravel, I've seen how it's done in Symfony, and I said, oh, that's how that works. Because you get to see the same domain space done in different ways. I understand the front end works the same way, but my JavaScript is not good. My JavaScript in the browser is even worse. So your guess is as good as mine what they're like, but they exist. And every time I blink, there's a new one that comes up. So yeah, I think it's quite good in that sense. But yeah, they are licensed appropriately for open source to actually be on that site.
Nice. So probably another question we got time for. In your opinion, what is a practical application of serverless?
Practical application, oh, there's a good question. Everything and anything. I mean, where do you start? The first obvious case is that you've got a static website and you need a little bit of logic. The best way to do that, put up a serverless function, let your JavaScript within your front end just talk to your back end, and now you've got some logic hidden away outside of the JavaScript for maybe doing authentication or something like that. Another good example, which I will take from my professional life, is I mentioned I do a lot of insurance. One of my clients does a scheme where all the insurance renewals happen on the last day of the month. And what we have to do as part of the project I was working on is we had to send an email out to every single person who's getting their renewal done on the last day of the month. So we had this project where we needed to do something like 25,000 emails in the 6 hours between 6 p.m. and midnight on the last day of the month, and had nothing to do for the rest of the month. This is an ideal serverless application because I don't have to pay for a server for 29 or 30 days of the month when I'm not actually using it. But I do want massive scaling for 6 hours. For 6 hours, I've got an awful lot of emails that need to go out, and the serverless system just automatically scales for me. I could have 1,000 concurrent instances sending these emails. And then it all shuts down again. I didn't even have to think about scaling. It just magically works. It's a lovely little use case, but it's extremely niche, but I quite like it.
All right. Well, hey, that was a fantastic answer. Rob, we're going to go ahead and wrap up your session and move on to the next person. Thank you once again so much for giving that presentation.
You're welcome.
All right. Take care, Rob. Okay. So before I go ahead and move on to Dr. Arjun Guha, I do want to make a quick announcement. So if you've been enjoying these sessions so far and you're interested in improving your serverless capabilities, in about 2 days, I'm actually going to be providing a free 30-minute webinar where I'll be teaching you the basics of programming with Nimbella. You'll be able to get your serverless environment set up in just under 2 minutes. You will deploy your very first serverless functions, and I'll even show you how to deploy your very first serverless app, all in the span of 30 minutes. So if you are interested in checking out that presentation and getting started with serverless, or you're looking for a quicker alternative for programming in serverless, definitely check out my webinar coming up in 2 days, and I look forward to seeing you there. Okay. So other than that, I'm going to go ahead and present Dr. Arjun Guha. So for those of you who do not know Dr. Guha, he is the Associate Professor of Computer Science at Northeastern University. And not only that, so in his presentation, he will be discussing speeding up serverless functions with language-based isolation. So if you build serverless functions and are looking to improve them, or you're looking for a good place to start, absolutely stick around for the next 30 minutes. Dr. Guha, how you doing?
Good. How are you, Jamie?
Doing great. So I will go ahead and share your screen.
All right.
All right. Take it away.
All right. Thanks. And before we begin, I'm happy to take questions at the end, like everyone else. But something that Jamie and I are going to try is to have me. I'm going to ask a couple of questions during the talk, and I'll be monitoring comments, and we'll see how that works. So when I ask a question, feel free to sort of answer it in the comments, and we'll see how this goes. Okay, so thank you all for coming. As Jamie said, I'm a professor of computer science at Northeastern University, and I'm going to talk about a recent research project of mine. This is joint work with Emily Herbert, who's my graduate student. So a little bit about me before we begin. Come on, click. So I'm a professor, an associate professor of computer science at Northeastern University since yesterday. Prior to that, I was a professor at the University of Massachusetts for several years. My research area is programming languages. And I've spent a lot of time thinking about various topics that relate to JavaScript. So back when I was a grad student, I spent a lot of time thinking about type checking JavaScript, done a bunch of work on functional reactive programming, a lot of work on static analysis and web security. I also work on something called software-defined networking, which would take a lot of time to get into, but it's something that's a lot of fun. More recently, I've been thinking a lot about WebAssembly as well, and of course, serverless computing, which is what I'll be talking about today. So today's talk is going to be a peek under the hood of serverless computing. We're going to talk at a high level about how serverless computing platforms like OpenWhisk are built. We're going to talk about some low-level factors that affect the performance and correctness of serverless functions. And I'm going to talk about a research project of mine, which is about transparently accelerating a class of functions, a class of serverless functions using certain tricks from programming languages research. So before I get into serverless platforms themselves, I think it helps to remind ourselves what a traditional web application looks like, which I'm sure many of you are familiar with this, but let's just context switch to an old-fashioned web application. Here we have, I guess a late 90s web application where the client is well, apparently running Netscape, and the server is running, let's call that PHP 4 or 5, not PHP 7, and the server is talking to some database. So this is a fine web application. This is the kind of web application I learned to write sort of pretty early on in college. And this kind of architecture works just fine, but it falls down and falls apart very quickly at scale. So with even a moderate workload, if this really is the architecture of your application, your web service will sort of go up in smoke with even moderate load. So what does a modern web application look like? Well, so here's a cartoon of it. So in a modern web application, you have thousands, potentially millions of clients. Most of your clients are mobile, talking to a firewall, and your firewall talks to a load balancer, and the load balancer distributes load across a whole bunch of web servers, and your web servers talk to a bunch of file servers and database servers. And the moment you have this many components, you need to worry about security, you need to worry about resource allocation, you need to worry about the cost of infrastructure. It's all extremely complicated, way beyond what I learned as a college student. And the promise of serverless computing is that you don't have to worry about any of this stuff. So all of this infrastructure is still important in serverless computing. It's all still there, but it's the cloud provider or the serverless platform that takes care of it. The promise of serverless computing is that the programmer just writes a serverless function using JavaScript, Python, even PHP, as we just learned. And the cloud infrastructure is hidden mostly from the programmer. So we're going to take a look at what happens under the hood. I think it's really valuable to have a high-level understanding of what's happening under the hood. It helps you understand the performance of your application. It helps understand correctness issues. And I also think it's super cool. OK, so let's get started. So where do serverless functions run? So when web requests come in to your serverless function, they hit some sort of, I'm calling it a dispatcher here. Other people have called it an API gateway. They hit some sort of web server or API gateway or dispatcher that's hosted by the serverless platform. And when that first request comes in, the dispatcher fetches the code. Here, let's imagine that the code is written in JavaScript. The dispatcher fetches the code for your serverless function, loads it into a container, and then proxies the request off to the container, which then runs your JavaScript code and sends a response back to the requester. So this is fine. So far, it looks very much like a traditional web application. But but the magic is what happens under load. So imagine that you suddenly get a flood of traffic, an enormous volume of requests. Well, what the dispatcher is able to do transparently is fire up new containers for you so that you can process requests in parallel. And it does this automatically, transparently, without any programmer intervention. In fact, under normal circumstances, you don't even know how many containers are processing are actively running your serverless function, and that's a good thing. So in addition to creating new containers, when traffic increases, imagine that traffic goes down and you're back to just processing a slow stream of requests. Well, after a period of time, the dispatcher will automatically shut these containers down. And in fact, if traffic goes down to 0, no one's using a function, after a period of time, the dispatcher will shut down all running containers, so your serverless function consumes no resources at all. This is called, people call this scaling to 0. Okay, so the programmer, the programmer, don't have any direct control over the number of containers that are running, though there are ways to sort of get in under the hood and have and understand what's happening by looking at logs, and we'll look at that in a moment. Okay. So to dive a little bit deeper, I'm going to sort of go through a quick little experiment. Here's this is like the hello world of a serverless function. This is a function that just responds with the string hello world to any request. I've written this to run on Google Cloud Functions. That's what I'm going to be using for all my examples. So I deployed this function yesterday evening, and then I sent 4 requests to it using curl, and then I fired up the log view, what is it called? Google Stackdriver logs. And here's the log. Here are the logs that I got. Okay, so as you can see, the first function took 76 milliseconds. The first request took 76 milliseconds, and the remaining 3 took 10 and 13 milliseconds. Why was that first one so slow? Cloud Computer makes a wild guess. If the subsequent, it was cached, if the subsequent request response was the same as the response was cached. So no, it isn't caching here. I took care to make sure that caching is busted. So really what's happening here is the cold start problem that the second talk talked about, and which is that when that very first request comes in, the container needs to get created, and creating that container takes a little bit of time. And that's what you're seeing. That's why it takes a little bit longer to serve that first request. And the subsequent requests are able to be served faster using the existing container. So this graph here at the bottom shows shows another experiment where what I'm doing is I'm running the same function, but what I'm doing is over a period of 30 seconds, I'm maintaining 40 concurrent requests. So on the x-axis here, you can see time, going from 0 to 30, and on the y-axis, I have the response latency on a logarithmic scale. So as you can see at the very beginning, sort of the mean latency is as high as a second, because that's the containers those are all the containers warming up. That's what drives the mean latency high. And as time goes on, mean latency sort of drops precipitously to, I don't know what that is, about 40 milliseconds. There's a blip here. Again, I don't really know what that is. But the point here is that it takes some time for containers to warm up, and there can be a lot of variation in mean latency. I should mention the dashed line here. The dashed line here is meant to represents maximum latency. So you can see that there's a lot of variation in response time. So there's this fundamental trade-off between performance and cost that we're seeing here. So if you're willing to buy lots of dedicated hardware or dedicated virtual machines, and you're willing to pay for a lot of computing resources that are mostly idle, and also pay for the complexity of managing and configuring all of that hardware, you can build a system that's very fast, but of course costs an enormous amount of money. Serverless computing gives you a much simpler abstraction. It's pay for use, but it can have lower performance than dedicated hardware. So what I'm going to talk about today is some techniques that we can use to perhaps improve the performance and lower the cost of serverless computing without changing the serverless computing abstraction itself. Okay, so the key trick that I'm going to use is that I'm going to try to avoid using containers as much as possible. Okay, so there's a couple of ways you can imagine doing this. So I'm going to talk about other people's work briefly. So one approach is to change the API. So Cloudflare Workers, for example, as far as we know, doesn't use containers. Instead, what they do is that they run serverless functions in V8 isolates. So they're all running in the same process, but sandboxed from each other using V8, the Google V8 sandboxing mechanisms, which are known as isolates. You can do something even more extreme than this. So, for example, JavaScript is fast these days, but you can go even faster. There's languages that are even faster. For example, there's a paper published at ATC 2 years ago that said, look, if you want serverless functions to run fast, stop using JavaScript, stop using PHP, stop using Python, use a language that's actually significantly faster, such as Rust. Okay, that would be another way of doing this. All right. So instead of going down these two routes, what I'm going to do is think about some of the other key attributes of serverless functions. And they're going to help us come up with an alternate solution which allows programmers to continue using the APIs that they're used to. OK, so I want to talk about some other attributes of serverless functions, and these have been discussed briefly in the two previous talks. So the first is idempotence. So when a request comes into a dispatcher, it may actually be duplicated, and 2 copies of the request may be sent to 2 containers, to 2 different containers. Any ideas for why this might occur? What might cause the dispatcher to actually create a duplicate request and send it off to 2 different containers? Doesn't seem like something that we would want. So remember, in practice, for the serverless system to scale, a serverless platform is typically running as a distributed system. And in a distributed system, the platform, or in fact the user, may retry a request that appears to have failed. And if the failure is transient, the request may actually be duplicated. And when that occurs, it's up to the programmer to ensure that their serverless functions are idempotent. So we heard about this a little bit today. So and if you Google for serverless functions and idempotence, this is what you'll get. So there's an article from Google. There's an article about idempotency in Lambda functions, and this idempotency is a property that matters in most of these serverless computing platforms. So another important property of serverless computing is that typical serverless functions are short-lived. So there was a paper presented at the Usenix ATC conference this year that was a measurement study of the serverless function workloads on Azure. And this paper found that half of functions complete in less than a second on average, and half of them actually complete in less than 3 seconds maximum. And I encourage you to look at this paper. It has a bunch of really interesting graphs that talk about what typical serverless workloads look like. So that's something else to keep in mind, right? So when you think about your traditional JavaScript runtimes, such as Google V8, they're really designed to run, they're really optimized to run long-running web pages and sophisticated interactive applications really fast. But serverless workloads are very different. And finally, I want to point out that serverless functions must necessarily be able to support transient in-memory state. Essentially, the serverless platform is creating and destroying containers automatically. And what you need to be able to do is thus write code defensively. So you don't know when your container will be started up or shut down. And what happens when a serverless function is shut down? What happens to the in-memory state? Sort of a trick question, really. Because your in-memory state just sort of goes poof, and it's up to you, the programmer, to make sure that your state is externalized and stored in some sort of external database. So just to summarize, serverless functions are typically idempotent, short-lived, and they have to be written to be resilient to being shut down at any time. So they have to be able to deal with transient in-memory state. And so what I want to think about is designing a new kind of serverless computing platform that's optimized for serverless functions that meet these criteria, while keeping in mind that we want to also support sort of a much broader family of serverless functions that aren't necessarily short-lived, that aren't necessarily robust in these ways. Yeah, cloud computing makes a good point. There is a trade-off here, and I'll talk about that in a little bit. Okay, So the idea that my research group has been investigating for about a year or so is an idea that we call serverless function acceleration. So it's a new kind of serverless platform that works as follows. When a request comes in to the dispatcher, instead of immediately setting it off to a container to sort of serve as usual, what we do instead is we have a fast path that's entirely within the dispatcher that we call the accelerator. So the point of the accelerator is that it's capable of handling a large class of requests much faster than a container. And if it works, great. Things have gone faster. But the accelerator is sort of optimistic and speculative. So there are cases where the accelerator fails to run the function to completion. And when that occurs, it's OK. We just move the request off onto the slow path, which to us is simply running the serverless function in a container, which is what's usually done. And the reason that this works is the reason that this works is that we rely on serverless functions being idempotent. So we take the request, we try to accelerate it, and if it fails, we simply retry it again in the slow path, which is the container. And so as far as the program is concerned, failing in the accelerators is just another transient failure, just like any other transient failure might be. Rob mentions that he's impressed that I can keep track of the chat window. I can barely keep track of the chat window, so I'm regretting it a little bit, but I'll try. Okay. All right. So so I want to talk about how you can about sort of the design space of an accelerator here. So as I see it, there's sort of three axes that we can think about. So one is, what kind of programming language are we going to support in the accelerator? In the extreme, you might want to support any programming language. I'm not going to do that. I'm a programming languages guy, so I'm going to use a language-specific technique. The other axis here is the acceleration mechanism. So how shall we accelerate serverless functions? And we'll talk about that too. And the final thing here is a security model. So the point of containers in a serverless platform is to secure the platform from potentially malicious serverless programs. So how do we ensure that code running in the accelerator itself is safe? Okay, so briefly, the accelerator that we've prototyped supports a subset of JavaScript. Its acceleration mechanism involves compiling to Rust, and its security model relies on the type safety of Rust itself. So let's take a look at this in a little bit more detail. So the language that we support, as I said, is a subset of JavaScript. And what we don't support is programs that access the file system, use Unix signals, or start other processes. So if you've used Cloudflare workers, these are similar sorts of restrictions that Cloudflare imposes on its serverless platform. Now, we have two additional restrictions. One is that we don't support programs that load code dynamically, so we don't support eval in JavaScript. And we require functions to run fast and consume limited memory. And then these are configurable parameters. But the point of acceleration is that if a function comes along and it violates any of these conditions, that's OK. We sort of fall back to running the function in the container transparently. So let's move on to the acceleration mechanism. So as I said, our acceleration mechanism involves compiling JavaScript to Rust. If you haven't heard of Rust, Rust is this systems programming language that's designed to be sort of a safe alternative to C++. And if you use, let's say, if you use Firefox, for example, there's portions of Firefox that are written in Rust. It has some really nice features that we exploit here. So compiling JavaScript to Rust is actually a terrible idea. There's this sort of impedance mismatch. Like JavaScript is this sort of dynamic, sort of anything goes kind of language with garbage collection and closures. And Rust is none of those. It has very strong type system, doesn't do GC, doesn't really have closures, and moreover, there's a sort of performance mismatch. Right? To make JavaScript code run fast, you need a JIT, which is the sort of runtime mechanism that all serious JavaScript platforms employ. If you actually compile it to if you actually statically compile JavaScript, you end up performing really poorly. So we don't actually compile JavaScript with Rust. That wouldn't work. What we do instead is a little more sophisticated. So what we do is we start off by actually processing requests in containers, which is how existing serverless platforms work. But we have this one special container which runs an instrumented JavaScript runtime that builds execution traces of the running program. So the execution trace, the execution trace of the program essentially has the sequence of statements and branches and loops that the program executed. So now imagine that a fourth request comes in. Now, if this fourth request comes in and it sort of produces exactly the same execution trace as we have already, well, we haven't sort of learned anything about the program. But imagine that it comes along and executes a different branch and goes down another trace. One thing we could do is we could generate a completely new execution trace. But what we do instead is we merge the new trace onto the old one. And so really what happens is that we build an execution trace tree. Now, you may be thinking, if you're sort of building these execution traces of the running program, it's possible that you won't actually witness every single branch that's in the program. And that's OK, as long as you know where they are. So think of these as execution trace trees with little, I call them bombs in them. And these bombs correspond to branches that we haven't seen while building the execution trace. And so if we ever encounter a bomb during execution, we sort of fall back to just running in the container. Anyway, so the point is that these execution trace trees can be compiled to Rust quite easily. So what we do is we extract these traces out of this instrumented container into the dispatcher and compile them into Rust. And now when a request comes in, it gets processed directly in the dispatcher itself within Rust and doesn't need to be proxied off to the container. Now, after a period of time, assuming that subsequent requests all fall on trace and don't actually trigger any of these bombs, the dispatcher will simply shut down these containers and reclaim those resources for other serverless functions or whatever else you may be running. So eventually, after a period of time, you're no longer running serverless functions in containers. You're instead running them directly on the dispatcher itself. So in an ordinary serverless computing platform, it's the container that isolates JavaScript from the platform. So what is it that isolates the generated Rust code here from the dispatcher code? So there's a combination of two things that's going on here. So one is static types. So Rust has this powerful type system that ensures that certain kinds of bad things can't happen. Seg faults, memory leaks, and so on. There's a whole bunch of caveats here that we can get into in glorious details. But basically, we're able to leverage the Rust type system in various ways to ensure that the Rust code, which is generated from the user JavaScript code, doesn't sort of do bad things when it's running in the dispatcher process itself. We can't guarantee everything statically, so we also insert in a bunch of dynamic checks. So for example, we kill functions that consume too much memory or run for too long. So to wrap up, I want to show you a quick graph. We have a whole bunch of other graphs that you can see in our draft paper. So what this graph shows, again, on the x-axis, so this is a serverless function. I forget exactly what this function was. It's something a little bit more sophisticated than hello world. There's like a database involved. So on the x-axis, we have time. So this experiment ran for a minute. And on the y-axis, we have latency on a logarithmic scale. So the red line represents the mean latency when we're running just containers without doing any of this execution tracing stuff. And the green line represents latency when we are doing execution tracing as well. So since in both approaches we start out by running functions in containers, latency initially is high because containers need to start up. We need to do that cold start. But after a period of time, you'll see that Rust starts and latency drops significantly because we're now processing requests in Rust. So mean latency drops significantly. That's what the solid lines are here. And if you look, and these dashed lines, as I had in my first graph, the dashed lines represent maximum latency. So maximum latency drops significantly as well. So there's a whole bunch of things that are not happening here, right? So we don't have that proxied request because we're processing a request in Rust. We don't have garbage collection because we're allocating values in an arena in Rust. There's a whole lot of less copying going on once we're processing things in Rust. So that's where this significant drop in maximum latency comes from. Running code in Rust also consumes far fewer sort of resources, both memory and CPU. And so this graph here shows that when we, sorry, the colors got inverted here, but when we run code in Rust, the CPU utilization also drops precipitously as long as we're on trace. So just to wrap up, so I wanted to give you a sort of a quick high-level overview of how serverless platforms currently work under the hood. Wanted to sort of emphasize that many serverless functions are idempotent, short-lived, and it's possible to build a radically different serverless platform that optimizes for these kinds of workloads. I described a prototype of what we call language-based serverless function acceleration. And the prototype is available on GitHub, and there's a link to our paper as well that describes what it does on detail. So thank you all for coming. I'd be happy to answer any questions if there are any.
All right. Hey, fantastic presentation. Thank you so much for doing that. All right. So you actually do have a few questions. So one of the questions you got, so in your opinion, what is the future of computing services?
May I reinterpret that as serverless and not computing services?
Yeah, sure thing.
So I think so what's exciting to me about serverless computing, so as a programming languages researcher, what's exciting to me about serverless computing is that it is more of a language-based abstraction. So because the programmer typically doesn't have access to a bunch of low-level things, like I don't think there's any serverless platform that actually lets you say do sudo, for example. So it's because the programmer doesn't have access to a lot of low-level operating system facilities, you can begin to play language-based tricks such as this, such as what I just talked about. So Cloud Workers is another example. They're running serverless functions written in JavaScript in V8 isolates instead of using operating system based isolation techniques. So I think we're going to see an explosion of various kinds of sort of creative ways of running serverless functions, and I think many of them will actually be transparent to the programmer. So unless you were really interested, you won't know how the serverless platform is running your function, and that'll be a good thing.
Nice. Oh, and you did get one question directed to you in the chat as well. So, one of the questions is, what is the cost effect when you go with the serverless approach? So I don't know if you know much about the money aspect of it, but if you do, definitely feel free to talk about it.
Yeah. So as a academic, I've had the pleasure of mostly not thinking about this. So my understanding is that if you the last time I checked, if you look at it as simply in terms of cost per second of usage, it's the last time I checked, it was more expensive than buying a dedicated VM. However, with dedicated VMs, you need to plan to have a lot of extra idle capacity to handle traffic spikes, and you of course have to manage all of that complexity. And so the cost equation is very complicated.
Yeah, makes sense.
Yeah, and when you think of cost of development, I think if you can get away with a serverless computing solution, you're better off. The cost of actually setting up something scalable using VMs is significantly higher.
Makes sense. So you did get another question about from the Stateful question that you had asked. We kind of built off that. So one of the answers you ended up getting was using some sort of cache like Redis. You want to kind of go more on that, like, what you prefer or anything like that?
Yeah, so I didn't get to any solutions. I sort of pointed out that it is a problem that you have to be aware of in serverless computing platforms. And I think the last talk of the day by Rodric will talk about the Nimbella approach. So stick around for that. Let me not get into solutions here.
Okay, I appreciate that. So other than that, so that concludes this session. I'm going to be moving on to the next person. And Dr. Guha, thank you so much for that. I really appreciate you coming by and giving this presentation, because I know, you're a professor. I know you're a busy guy. So appreciate you taking the time to do this for us.
Take care.
Take care. Okay. All right, so the next person we have. So it's actually interesting introducing this person, because if you've ever actually gone on Twitter and searched up the word serverless, you've probably seen this guy pop up. So Jeremy Daly, if you don't know him, he is a serverless consultant and AWS serverless hero. And when he's not doing that, he is actually the voice of Serverless Chats, which is a podcast dedicated to keeping people up to date on serverless technology and bringing people on board to talk about their aspects of serverless technology. So if you're wanting to learn more about that, that is absolutely a podcast you should check out. Jeremy, how are you doing today?
I'm doing really well. Thank you, Jamie. Thanks for having me here.
Oh, of course. Well, I will go ahead and get you set up. All right.
All right.
And
thank
you
you.
Go ahead and you can get started.
All right. Well, thank you, Jamie. Thank you, Nimbella. Thank you, everyone, all the organizers, for having me here today. And thank you for everybody who's watching. So we're going to talk about building resilient serverless systems with non-serverless components. I know you heard a lot of serverless talks so far today. This one's going to be very, very hands-on. We're going to talk about actual solutions and ways in which you can mitigate or start introducing serverless into your applications. So a little bit about me. I am an independent consultant. I've been doing this for a very, very long time, which is why I have all this gray in my beard and my hair. I started working with AWS in 2009, so very early on in the EC2 revolution there. And then once Lambda came out in 2015, it was GA. I started building a lot of things in serverless. I also blog. I do a lot of contributions to some open source projects. I do some speaking. Clearly, I have a newsletter that I write every week that basically wraps up the what's happening in serverless across the industry. And I put that into a newsletter every week that's off by none. You can check that out. And then finally, like Jamie said, I host a Serverless Chats podcast. And I also have a new series coming out called Serverless Spotlight. So that's something to check out. And again, as Jamie mentioned, I'm an AWS serverless hero. So the agenda for today is pretty packed. So I'm going to go really fast through this, and hopefully you can watch it back on half speed if you need to. So first, we're going to talk about what is resiliency, and we'll go over quickly what serverless is in the context of what I'm talking about. We'll talk about working with less than scalable relational database systems. We'll talk about using unreliable APIs, managing API quotas, decoupling our services and how we can employ some of these techniques by decoupling the services, and other non-serverless components that we might run into. So first, I want to talk about resiliency. This is very different than reliability. Okay, so resiliency is this idea that you can have failures, but that your system can somehow absorb those, and you can continue to provide some acceptable level of service. So this is not about preventing failure. This is about mitigating it or being able to gracefully deal with it. So that's an important aspect of what we're going to talk about today. If we talk about what it means to be serverless, again, we're at a serverless conference, so I'm sure most of you know, but these are the typical things we hear: no server management, flexible scaling, pay for value, automated high availability. Those are sort of the things we hear. Those are the marketing terms. But other things to remember about serverless is that it is a lot of configuration and knowledge of individual cloud services. So serverless goes way beyond just functions as a service. We're talking about other managed services and other components and tools that we can use to build these applications. And you need to know those. You need to know how those connect. And finally, it's highly event-driven. So we are not talking about our typical synchronous invocation. We hit a server, we hit a database, when we get that data back. We're talking about distributed systems. We're passing a lot of events around. So this is just something to think about when we're building. And this is what part of what we mean by serverless. So today we're going to focus mostly on the scaling aspect of it, okay? Because serverless, we hear that it is very flexible scaling, but we need to think about how that relates to the other services that we might be interacting with that don't scale quite as well. So I'm going to talk a lot about the AWS ecosystem here, right? So if this is a bit of a shock for some of you that we're looking for some more open source stuff, I'm more familiar with AWS, and they're further along when it comes to some of the other services that they've built around this than some of the other cloud providers. So most of this is going to be in the context of AWS, but a lot of it does translate to a lot of the other cloud providers. So in the AWS ecosystem, they think about serverless as these services that you can just throw work at. You don't have to worry about provisioning or any sort of capacity planning. You can just throw work at them and they will scale, and there's no management involved. On the other side of the coin, you have these things called managed services, and a lot of other cloud providers have things similar to this, where these are services that you don't have to manage, you don't have to patch them, you don't have to worry about, restarting servers and that sort of stuff, but you do have to worry about capacity planning. So we have to think a little bit more about how we're going to utilize these different services. And then finally, you have the things that are not serverless, okay? So these are things that are running on VMs, anything on EC2 or Google VMs or some of these other things, and anything installed on top of that. So even Kubernetes or Docker or something like SQL Server or MongoDB, if they're running on top of EC2 instances or virtual machines and you have to think about those, then we're going to consider those to definitely not be serverless, right? So we're going to stay focused mostly on the two to the left here. All right, so we're going to talk about limits. So everything has limits, and this is something important. So even if you think serverless can scale infinitely, you still have things like reserved concurrency. You still have timeouts on functions that can only run so long. There's memory limits involved. And then with any distributed system, because we're passing messages around, we need to think about network throughput, and that's going to be a limit there. Now, depending on what component you're using, what service you're using, some of these are better than others. Some of them scale better than others, handle more requests and so forth. But the important thing here is just to know your limits, okay? Everybody that does this, every cloud provider publishes their limits. AWS is very good about this. Azure is very good about this. So you can know what the limits are of these individual components. All right, so let's jump into an actual example of something that I consider to be a simple serverless web service. And in the context of AWS, we would use an API gateway. We would call a Lambda function, which is their functions as a service, and then DynamoDB, which is a managed NoSQL database that just scales very, very well. So the thing that's great about this is API gateway is extremely scalable. Lambda functions are extremely scalable, and DynamoDB is highly scalable. But if you remember the band Dire Straits way back in the late 70s, early 80s, they had a song called Money for Nothing. And in that song, you may remember this line, I want my SQL. And they make a very important point here because developers are not willing to get rid of SQL databases, MySQL, PostgreSQL, MariaDB, those sort of things. So if we look at our simple serverless web service and we swap out DynamoDB, that highly scalable NoSQL, for RDS, which is the relational database service that AWS offers. So again, MySQL, MariaDB, Postgres, something like that. The problem is that this is not that scalable. And when you couple that together, then you sort of have this simple, not so serverless web service. And part of the reason this happens is it has to do with how relational databases and fast sort of relate to one another. And a function as a service has a different concurrency model than you might have if you were just hosting a server. So you can't use connection pooling from a Lambda function or from an Azure function or some of these other types of fast because they have to actually have a separate container run for each concurrent invocation, which means that when you connect to your database, you need to have a single connection per concurrent invocation. So that can really tie up those DB connections, and you're going to have a limited number of database connections. So let's say that you have 1,000 connections or something like that. If you have 1,000 concurrent Lambda functions, you're using all 1,000 connections, which can really wreak havoc on the CPU. And then the other problem you have is because of the way that fast interacts with any type of relational database, it has to keep that connection open. And the way that most of them work is they'll freeze that connection in between invocations. So you're not paying for something running to keep that connection open. But when that Lambda function does fire off again, it will have that connection maintained. That's a good thing, but also a bad thing if that connection goes away or if the function goes away, because you have recycled containers that then create these zombie connections that need to eventually be cleaned up. All right, so there are a couple different ways that we could manage these database connections from serverless functions. One thing we might do is increase that max connection setting. So again, maybe we have 1,000 connections available on our current, our current cluster. We want to bump that up to 3,000. This is typically a bad idea because you are going to spike your CPU if you're using too many connections. So it would be much better to use connection pooling, which we can't necessarily use. So the other thing that we could do is we could limit concurrent executions. We could just tell our clients, hey, sorry, we've got 500 people using it right now. You're not going to be able to process your request. That can tend to make people upset. You could lower your connection timeouts, hoping those zombie connections might clean up. Again, that's sort of a cross your fingers approach. You could limit connections per username. This is sort of a game where you say, okay, this particular piece of the application gets this many connections and this gets this many connections or whatever. Typically not a great idea. And then you could close the connections before the function ends. This is a terrible idea, setting up a new MySQL connection from a Lambda function. You typically only want that to happen on a cold start. That can take 100 to 200 milliseconds. You don't want that to happen on every single invocation. So we're going to say these are bad ways that we want to manage the DB connections. So what are some better ways that we can do this? So first of all, we could implement a good caching strategy, go back to Computer Science 101 and think about caching. We'll get into each one of these individually, so I will go over these. You could buffer events so that you can add some throttling and some durability so we don't necessarily lose messages. And then you could potentially utilize a proxy service, and there's a couple of these services that are out there now, or you could manage the connections yourself, add a little bit of code to do that. So these are better ways to do it. So let's look at each one individually and see how we would implement these. So caching, implementing a good caching strategy, again, in the context of AWS, we want to connect to our relational database. Rather than connecting to it directly, we would add something like Elasticache. Elasticache is the AWS service that gives us Redis or Memcache. Any caching service would work. And so what we would do here is when a request comes in, now this is going to be for your heavy read application. This is if we are, we're doing a lot of GET requests. So what we would do is we would call the Elasticache and check to see if our key was in there. If we get a hit, great, we can respond right back to the client. But if we have that same request or a different request come in, and this time we get a miss, then clearly we have to query the database, pull the data back. Elasticache, most caches you're going to deal with, Redis, anything like that is not going to be a write-through cache. So we are going to have to write code that's going to update that cache for us. Then we can respond back to the client, and then the next time we get it, we should have that in a nice warm cache. Couple of things to think about here. We only want to connect to our RDS database or to our relational database when we have a miss. So we don't want to always set up that connection. It is possible that if you have a nice warm cache, that you might not even need to hit the database at all, depending on I guess how how differentiated your data is and how many different types of the carnality of the data. So the other thing you want to do is make sure we set low TTLs. This is just basic caching. And then we want to include the ability to validate the cache. So we do want to make sure that if we are doing any type of application that's writing data to the database, that those are clearing those keys when that happens. Now, if you're looking at this and you're saying, we seem to be adding a cache here because our database can't necessarily handle the number of connections that we need to make to it, I would totally agree with you there. And if we look back at our, again, early computer science classes, I'm sure our professors told us that we should not be adding a cache in order to, prop up our database. And we're not really doing that here. We still need to size that database appropriately. So if you're assuming about 1,000 connections to your database, you still want to be able to make sure that that database is sized to handle that. The idea of the cache here is sort of twofold. One, it helps with mitigating that connection issue. And the connection pooling issue is not a problem with relational databases. It's more that the connection idea or the connection strategy here is broken when it comes from fast to RDS or any type of relational database system. And then the other side here is that if you have a nice warm cache, that you build in a little bit of resiliency, because it is very likely that at some point that relational database is going to go offline, it's going to slow down, or something's going to happen where if you do have that cache backed up, we can have a little bit of resiliency added there, and it's just always a good way to do it. All right, so then the other question is let's say we're talking about a high write or a high throughput write application, maybe a webhook or something like that. We need to ask ourselves whether or not we need immediate feedback from our downstream system. And if we think about the typical way that we build applications or have been building applications, we are very familiar with this synchronous communication pattern. That's when our browser calls a web server, the web server calls the database, does what it needs to do, responds to the web server responds back to the client, to the browser. The problem with that is that it's a blocking request, and everything in that chain has to work perfectly in order for the client to actually get what they need. But when we start building distributed systems, we have to start thinking about something called asynchronous communications. I'm sure you've actually heard a lot of this now, especially if you have kids we can send a request somewhere, have some intermediary service that is much more lightweight than the final downstream process, be able to capture that and say, I've captured this information and now I can pass it along when it is appropriate or when it's possible to do that. So if you look at something like a webhook, all right, and we have a client, it's sending data to an API gateway that's using Lambda function, a serverless function to capture that data. We want to get that data into RDS. The problem is if we try to write that into RDS at the time it happens, we have the issue of what happens if we send out an email with 100,000 people on it and we get all these webhooks coming in that say, we just opened a message, or, somebody clicked through a link or something like that. You're likely going to run into a problem where that RDS cluster is going to get overwhelmed. You're going to crash that cluster. You're going to lose every single event that happens there. So what we want to do is two things. We want to make sure that we have durability in our messages, and we want to make sure that we can throttle that so we don't overwhelm that downstream resource. So what we would do is put something like an SQSQ. Now, SQSQ is an AWS thing, but think of RabbitMQ or any sort of lightweight queue that might be able to sit between, that would be able to sit and process messages and add that durability. So what SQSQ would do is it would actually accept a request from Lambda. I say asynchronous. It's not really asynchronous, but in a sense it is, in that it takes that, acts back to the Lambda function. You can immediately respond back to the client and say, hey, I got your webhook request for this email open or whatever it is. Then what we can do is add another Lambda function in here. And this Lambda function, and again, you have this ability with most FAST, the ability to set the concurrency. So we're going to lower this concurrency so that we do not overwhelm the RDS cluster. And then what happens is the Lambda function pulls that SQSQ, and it is a synchronous request, meaning that this stays connected the whole time. We put the data in RDS, RDS responds back to us, and then we can tell the SQSQ we got that message and it is removed from the SQSQ. And so what happens is that we now have removed it from the SQSQ. We've buffered that. We had that durability. The message got in there. And if there's a failure, then we can actually set what's called a redrive policy in SQSQs. And I'm sure other queues have similar things where if it exceeds a certain number of retries, we can actually send that to another queue and store that message to look at it later and inspect it and figure out what we want to do. So a couple key points here. SQS adds durability. I noticed Cloud Computing said that we can make our queues durable. I think okay. Anyways, so SQS adds a bunch of durability. Any type of queue that has some resiliency and redundancy in it would add some durability. We can add those throttled lambdas to reduce that downstream pressure, right? So we don't have to worry if that database goes down, we can still buffer those events we don't have to wait for, or we don't have to always have that RDS cluster available to us. And anytime there are failed events, we would store those so we can look at them later and potentially replay them. So again, database goes down, maybe there's a scaling event, maybe there's a hiccup somewhere, and we have thousands of messages in our DL queue, we can go ahead and replay those later. Now, with AWS, you actually don't need this Lambda function here. You can actually use something called service integrations that'll send the data directly to SQS, and then you could do whatever formatting or validation within that throttled Lambda function downstream. And you can actually do this now with both the REST API version and the HTTP API versions. If you're familiar with those, they just recently added it to the HTTP APIs. All right, so utilizing a proxy service. And again, I know I'm going fast here, but I do want to get through all of this. So there's something out there called PG Bouncer. That's something where, again, you connect to that, and that will manage your connections and do the connection pooling for you. There's something called SQL Relay. I haven't played with this, but I have heard some good input on it. And then the problem, though, with both of those is that you would have to install those on some sort of VM. So if you looked at this in the context of a serverless application, we're essentially adding, a VM in a serverless application, and that isn't the best thing to do. I mean, I guess what we could do to make it a little bit more serverless is maybe add in something like Fargate, which is a serverless container service, maybe similar to Google Cloud Run or something like that. And then the other option is if you are in the AWS ecosystem to use Amazon RDS Proxy, which is a new service that just became GA. So I want to talk about Amazon RDS Proxy, what it does, what it doesn't do. It is very cool, but it is definitely not a silver bullet for managing these connections. It does pool and share database connections. You can reroute requests on failover. So essentially, rather than using DNS or something like that to fail over to a backup cluster or an active cluster, you can actually do that through this service, which actually makes it a little bit easier. You use IAM credentials for the access control. So you actually store, you don't have to store your credentials for the database in your serverless functions or within some sort of system there. And then you can go ahead and just send that through. And it does this cool thing called connection pool maximum connections. So if you do have multiple systems or multiple applications using the same database, you can control each one of those individually. All right. Couple caveats though. It only works on Amazon RDS, and you still need to do capacity planning, right? So you still need to understand how it doesn't scale for you automatically, and it is an added cost. So you do have to pay a little bit extra in order for that to be supported. But if you are in the Amazon ecosystem and you want to quickly mitigate the issue with too many connections, this is a really, really good way to do that. All right. So moving on to managing connections ourselves. This is something where we would have to count the open connections, close connections if there's a threshold exceeded, close those zombie connections, and then do some sort of retry so that we could reconnect if there weren't enough connections available at a particular time. So you'd have to be crazy to build something like this because it seems like a lot of work. I was crazy. I built this. Now I'm showing this to you. This is a project that I built called Serverless MySQL. This is used by a lot of people. I'm showing it to you not because I expect you to use it. I'm showing it to you because I want to just explain the reasoning behind it and how I was able to mitigate those connection issues implemented in MySQL using Node. So again, if you're using Python or something else or Postgres, you're out of luck with this project, but you can at least look at it and see how it works. So the first part is that we have to count open connections. Very easy with MySQL. We just have to use the process list, get the number of active connections that are connected there. Then we can look and see whether or not we've exceeded some sort of ratio here. We can calculate whatever we want our timeout to be. And then we can try to kill zombies if we're running low on connections. But then if there are no zombies and we just are over our connection limit, then once we're done with our connection, we can just go ahead and terminate that. And then finally, again, just try to kill whatever zombies are out there. We want to then run a process where we can close any of those sleeping connections. So we set some threshold there. We say if a connection is open for more than 5 minutes and it's not being used, then we're going to go ahead and close that. And then we can just issue a kill command and kill those zombies, which is pretty easy to do. And then if we're trying to connect with our client, what we want to do is if we get some sort of error, we want to retry with some sort of exponential backoff. Probably not something that is just that is retries after a second, then 2 seconds, and 4 seconds, and whatever. You just be hammering it. So we use something like jitter. This is something I believe AWS came up with that just staggers those requests, adds a little bit of randomness to it. So the question is, does the type of approach really work? Well, in this implementation, I use an Aurora serverless cluster with only 90 connections available, a gig of RAM in my function. I simulated 500 users per second for 1 minute with an average response time being about 41 milliseconds, which isn't too bad. And there were 0 errors. Hold your applause. It's not, it's exciting, great, but this is a way that you could potentially do it. Now, if you are using MySQL and you are using Node, this will work with any, basically any cloud provider out there that's connecting to a MySQL database. So it is something that you could potentially try. But we shouldn't have to do this, okay? So there are services in Amazon that are doing some of these things. And again, I know this is a little Amazon heavy, so I apologize for that. But again, it's what I'm more familiar with. But there is a service called Amazon Aurora Serverless. This is a great service. It scales automatically for you. It handles MySQL, it handles Postgres, but this does not solve the maximum connection issue. So it essentially would just keep scaling up to larger and larger, what they call ACUs, in order to handle those extra connections. So actually, this in combination with something like the approach for serverless MySQL works really well. There's something called the Aurora Serverless Data API. I really, really love this service. It's an HTTP connection into a serverless, into a MySQL database or into Postgres. It connects to an Amazon Aurora Serverless cluster. So it does scale really well and it handles all that connection pooling for you. But it's kind of slow. So you can't really use it for synchronous workloads, but for asynchronous workloads, doing some background processing works really, really well. And then finally, we talked about the Amazon RDS proxy. Couple things here. Added cost, doesn't auto scale for you, so you still have to think a lot about capacity planning, which kind of defeats the purpose of service altogether. All right, so moving on to third-party APIs. If we're going to manage those calls to third-party APIs, very, very similar to working with something like RDS. So we can still implement a good caching strategy if we're doing a lot of read-heavy things, and we know we can, use a little bit of, have a small TTL so that we're not always pinging that API. That's not a bad way to approach it. We can buffer events for throttling and durability, just like we did. Put some sort of a queue in front of there, minimize, change the concurrency so that we're not overwhelming some sort of downstream API. And the other thing we can do, this is a popular way to do it, is to implement what are called circuit breakers. So a circuit breaker is a very common pattern with distributed systems because the idea is to say, we do not want to overwhelm some downstream API, especially if it starts slowing down. The worst thing you can do is if you have an API that's slowing down or throwing errors, the worst thing you can do is throw more work at it. So in order to implement something with like a circuit breaker with AWS, we would use, an API gateway, calls a Lambda function. And let's say we want to call the Stripe API. Now, the happy path here is we just call that Stripe API directly. That does what we want it to do. It responds back and it gets back to our client. But if you're familiar with the CTO of Amazon, Werner Vogels, he says that everything fails all the time, right? And we know that the Stripe API, of course, is notoriously unreliable. That's not true, but a lot of the APIs you work with probably will be. So instead of trying to call it directly, instead what we're going to do is implement some code within our Lambda function or within our serverless function that's going to do a status check. And we're going to use some sort of cache, right? This could be DynamoDB, this could be Elasticache, this could be Redis, this could be something else, whatever you want to use for this. And essentially, we're going to check that to see whether or not the circuit is closed. If the circuit's closed, then we get a positive status check. We can go ahead and we make that call to the API, and then if that's successful, comes back to the Lambda function, goes back to our client, everything's fine. Now, if you think about circuits, electricity, when it's closed, that's when the electricity flows through it. When it's open, that's when the electricity can't flow through it. So let's say that we get a situation where we get a failure from the Stripe API. It times out, it gives us some sort of error, whatever it is. What we want to do is we want to be able to actually increment that cache, increment some sort of failure count to tell it, hey, we just got a failure. And then once we do that, we can immediately respond back to our client and say, hey, sorry, we have an issue. We can't process your request right now. Now, again, your client could be an SQSQ. It could be all kinds of different things. It doesn't have to be going through an API gateway. There's a number of different ways that it could process that. So what we do want to do is once we get a certain number of failures, then we actually want to go ahead and flip the switch so that when a new message comes in or when a new request comes in, we're going to come back and say, sorry, we can't accept requests right now. The API isn't working. And that's when we flip it to the open state. And then we immediately respond back to our client and let them know, hey, we can't actually access the service right now. Now, of course, we can't do that indefinitely. At some point, we have to do what's called a half open. And this is where we basically just send a test request to the server, to the Stripe API or whatever the API is. Now, if this fails, it doesn't matter. We just respond back to client saying, sorry, it's still not working. But if it succeeds, then what we want to do is we actually want to update our cache and let it know, hey, we're back in business. We go ahead and flip the status check where our circuit is closed again, and it keeps working. So a couple key points here is with something like a serverless function, you want to try to cache your cache with warm functions. So you're going to spin up the same function over and over again. Most likely it's just going to be, it's not going to get recycled immediately. So if you can store some information about how many failures there are in there, that's a good idea. You don't want to necessarily be hitting your cache every request. That could get a little bit busy or expensive. You want to use a reasonable failure count. This again has to do with the velocity. If you have 1,000 requests per second, then maybe 1,000 requests failed is the right number. If you have 1,000 requests per day, then maybe 3 requests failed might be the right number to to flip your switch. The other thing is to understand item potency. There's a lot of reasons why a request could actually make it to the Stripe API, but then you don't get the data back and you're not sure about it. So you consider it a failure and you send the same request over again at some point in the future. So just understanding item potency is a good way to kind of get your head around making sure you don't send the same messages over and over again. Stripe API actually has a really good thing called an item potency ID. You could use a message ID or some sort of hash of the message to make sure that it doesn't reuse use, or it doesn't process the same message twice because you don't want to charge a credit card more than once. All right, so thinking about quotas quickly. Concurrency has no effect on frequency. So let's say that you have a quota of 50 calls per minute. Setting your concurrency to 50 isn't going to do any good if it only takes a second to process each request, because then you're going to be processing thousands of requests in a minute when you can only do 50. The other problem is that stateless functions, any sort of serverless function, is not going to be coordinated, meaning it can't necessarily talk to another one to see what its status is. And then step functions, which is a service with AWS has that does state machines, they get very expensive if you were to do something like this. And if you were to add state to each function, meaning you were to query a cache or something like that, you would still have to run each invocation. You would just check and say, oh, I can't actually call the API. And if you're doing that thousands and thousands of times, now that you're over quota, that's not very efficient. You're going to have a lot of extra things there. So if you thought about it and said, hey, can we build some sort of a better system? It would have to be serverless. It would have to be cost effective. It would have to be scalable. It would have to be resilient. And it would have to be efficient. And finally, it would have to be coordinated. So I have this pattern called the Lambda Orchestrator. I'm running out of time, so I'm not going to go through this in detail. There's a QR code there that you can find the story on my site that'll explain how it works. But essentially what this is doing is it's using a single Lambda function that is polling a queue and using DynamoDB as a cache. Again, this could be Redis or whatever. And then just implementing this thing called the fan out pattern that allows it to send out all of the current requests that are being processed. This has a lot of failure modes built into it. You've got SQS queues if things fail and are bad messages. If you're over quota and the message goes into one of the Lambda workers there, you can send it back to the SQS queue. Again, I wish I had more time. I would explain this in detail. But essentially, it's just a way that you can implement that circuit breaker pattern. You can make sure that you're not going over that quota, and you can make sure that all these things are coordinated so that you can work through a queue of messages, but still have it 100% serverless. So I want to get into decoupling our services here. This is an important thing that we want to be able to do because each individual service that we work with is going to be a little bit different in terms of how it scales and what patterns and what types of functionality we can implement into it. So there's a service called EventBridge. This could be something, this is something like Kafka or any of these things that might be, message buses. I think Azure has a message bus that you can use that's very similar to this. And essentially what you do with something like Amazon EventBridge is you can send requests to it and put messages or events into this bus. And then again, with EventBridge, you'd actually get the event ID back that you could use for tracking. But what you can then do is write rules that distributes these messages to multiple endpoints. Multiple Lambda functions, to step functions, to other event buses, to queues. And actually with EventBridge, you've got like 16 others that you can do, which is pretty cool thing because there's a whole bunch of other services you can trigger from it. And then again, as I said, each one of these routes, you can put rules on that says only send messages to the SQS queue if it's an event type of this or whatever. So a couple key points here is you can allow multiple subscribers to the same event using rules, patterns, and filters. So there's actually a lot that you can do. You've got like less than and great, less than, equal to, greater than, all those sort of things that will allow you to write really complex rules if you need to. You can forward them to other accounts, which is cool. If you're using AWS, a really good way to create bulkheads is to put microservices in separate AWS accounts. And then that separates, that gives you another layer of security. You can actually forward messages back and forth between different accounts, which is a good way to do it. And you do get 24 hours of retries with this, so it's very unlikely that you'll lose messages. There are no dead letter queues or things like that, but for the most part, it's pretty good in terms of the amount of retries that happens there. And then what you can do with an architecture like that is really great. Because what you have the opportunity to do is you can go ahead and accept some sort of a message or a web request. Let's say somebody posts an order. So I submit an order and say, here's my order 1, 2, 3, or whatever it is. Rather than trying to write that to a database or send an email message or do something like that, you can actually send that to EventBridge. EventBridge will immediately respond back and say, hey, I got your order, right? That's what your Lambda function can do. Now, I'm sure everyone has seen this a million times. You order something on Amazon or on Wayfair or whatever. It says, okay, great, we got your order. It's not actually processing your order yet. Instead, what it's done is it's now distributing that to its back-end distributed systems. So now we could take something like an order service. It's a standalone service that has no idea what is happening with anything else in the system, but we have like an SQS queue, for example, where we can use that buffering pattern, and we can write a rule that sends that whenever a message comes in that says, hey, this is a new order place, the order service picks that up, writes it into the SQS queue, and then goes ahead and processes it. And again, maybe the Lambda function has to be throttled so that we don't overwhelm that RDS system. Maybe it's a downstream system, an existing system that you have that processes your orders. But we can then also add like an alerting service. So now we can have another rule that says, okay, if this is an order complete, then we want to go ahead and buffer that event and then eventually send it to our Twilio API to send someone a text message. Maybe we have our billing service. So we have our Stripe API and we buffer that. And so then a message comes in and says this order was $50, and we go ahead and we process it that way. Now, again, these individual services are going to be a lot more complex than this, and maybe you have other Lambda functions there doing different things. But the point here is that writing rules like only trigger this if this order is complete and only trigger the billing service if the total amount is greater than 0 gives us a lot of flexibility in terms of distributing those things and then implementing those individual patterns that we talked about and utilizing the best one for each individual service. So key points here are going to be that we can filter those events to selectively trigger services. And again, let's say you have a marketing service that you want to add to this that just captures, leads or something like that, or a coupon service that can be added on without changing any of your other infrastructure. You can manage those throttles and those quotas per service. So use whatever pattern or whatever strategy you want within each service. And then we didn't talk about this. This is sort of, if you're using asynchronous services, a thing called Lambda Destination, which is pretty cool, but it's very AWS specific. So I'm not going to go into it. So if we think about some of the other non-serverless components we might run into, managed services. So we talked about those managed services before. That could be anything from an Elasticsearch cluster to maybe maybe even something like Fargate or something else that we're using that is a service that we have to provision, but we don't necessarily have to manage. We do have to think about the scalability of those. So those are components that we're going to have to mitigate the amount of traffic that we send to them if we have very scalable serverless components in front of those. You have other cloud services. So again, I mentioned Elasticsearch, but maybe MongoDB Atlas or something like that. Those may scale as far as they need to go, but there are a number of reasons why you might not have them scale as much as they want to. So you have to think about mitigating those as well. Legacy systems, this is going to happen all the time. If you're in the enterprise world, or even even some of the small and medium-sized businesses, you have some old billing system that you use. You have some CRM that you're using that maybe doesn't scale very well, but you do want to implement something where when somebody fills out a contact form on your website, you want that processed by a serverless function and sent to that legacy system. You have to think about mitigating that. We have our own serverless APIs, and I have a little, think about it there. Oops, let me go back for a second. The idea of our own serverless APIs is we may be setting quotas, or we may be setting some sort of limits because we want to be careful about, denial of wallet attacks or whatever. Maybe we don't want it so that you can have 10,000 people hitting an API at once. Maybe we do want to limit that for some reason. So bottom line here is that as we build serverless, we are a long way away from everything being serverless. So our serverless components are going to be, or non-serverless components are going to be inevitable. So you just need to make sure you know the limits of those components. You need to make sure you use good caching strategies when you're doing heavy read applications. Embrace these asynchronous processes, okay? There's no reason why things have to happen immediately. It can take a little bit of time. And when I say a little bit of time, sometimes we're talking fractions of a second to make some of these things happen. If you can buffer and throttle those events, it's more important to capture the event and do the processing later than it is to try to do that processing immediately and then lose the event if for some reason there's a failure. Again, this doesn't work in every situation, but depending on your use case, that's how you might want to do it. And we didn't talk about utilizing eventual consistency, but this is just something that is just a part and a completely acceptable thing within distributed systems. And what eventual consistency means, if you're not familiar with that, is essentially that we're not going to update that database instantaneously. It may take 30 seconds. It may take 5 seconds or whatever in order for that database to eventually get updated. But that's okay. That's something that we can deal with. It happens all the time. And it's just something that is part of distributed systems. So don't worry about that. All right, so thank you very much for having me. These are a couple of links to the things that I'm doing, my blog, the podcast, the newsletter, a couple open source projects, my GitHub, and then please follow me on Twitter. I am always tweeting about serverless. So if you have some questions, I don't know if we have any time left, but thank you very much.
All right, Jeremy, fantastic presentation. Thank you so much for that. Okay, so we do have a little bit of time for some questions. You've got a few in the chat. One of them was, how can you identify the maximum DB connection supported? And that was by Oscar.
Yeah, so it depends on what service you're using. So you can do, I'm trying to think of what the command is, but you can do, I think it's if you select at max_connections or something like that for a MySQL database, that will give you the number of connections. I'm not sure how to do it with Postgres, but there is, I think, another thing within MongoDB that allows you to do that as well. So those, if you look that up, you can find that pretty easily. It's documented well.
Okay. Another one, for circuit breaker, can we use service discovery patterns? And that question was asked by Cloud Computing.
Yeah, I mean, it depends on what we're talking about with service discovery patterns. If you mean the ability to maybe shift, if you have one service down, can you kind of shift that over to another service? That is possible to do. So I actually did that with one of the projects I worked on. We were using the IBM NLU, which is the Natural Language Understanding API. And we had set up one, I think it was in the South region or whatever. And every once in a while that would go down. And when it would go down, it wouldn't go down for like a few minutes. It would go down for hours. And so what we ended up doing was setting up another location in Germany. And we used that as the primary one in the south of the US. And then if that went down, then we actually would just reroute that within the code to that. So there is a lot of things that you can do with that, with that circuit breaker pattern. I mean, one of the things you can do is you could always try to be hitting your API, but then maybe you want to change it so that you actually cache some of the responses. So if you are, implementing a caching strategy along with the circuit breaker strategy, along with service discovery, you could say, hey, if this doesn't work, try this one. If this doesn't work, see if we've got something in the cache that we can at least serve back to the user. So again, those are really interesting patterns that you can use. It just depends on how complex you want to get and what you need, or what sort of level of service you need to provide to your customer.
Awesome. All right, so we have time for one more question.
Okay.
So in your opinion, how have you seen developers or operation teams be impacted the most by transitioning to serverless?
Yeah, so I mean, I think operations teams have been able to actually start working on more automation. So I love automation. The more you can automate with serverless, the better. And again, within putting my sort of AWS experience hat on, even if you are building out applications that are using something like relational database, or you're using RDS, or you're using EC2, or you're using Kubernetes, or using any of those things, you see a lot of developers or a lot of ops people writing code using Lambda in order to process events. So you have an entire stream of data that comes off of the AWS ecosystem that can trigger Lambda to do things. So there are people who write scripts that shut down servers at night, development servers at night when they're not being used. You have people who take, when there's some sort of an alert that comes in that might be something to do with a security alert, they take that, they use a Lambda function, they process that gets distributed via SNS or something like that. And then there's a lot of auditing that can be done. So I do think that the impact for ops people is that now they can focus more on making sure things are repeatable, making sure that they're not missing things, and spend less time worrying about trying to keep the servers up and running. And again, even if they're moving towards more serverless stuff, and your team is moving away from EC2, there's still plenty of things that need to be done that go well beyond what you would probably ask of your traditional developer.
Okay, well, hey, thank you so much for answering all of my questions and also giving this presentation. It was fantastic from beginning to end. We're going to go ahead and move on to our next session, which will be our last section for this 3 hours of serverless. Jeremy, I hope you have a great rest of the day.
Thank you.
All right, so we got Rodric now on board. So to give a quick kind of introduction, if you've been following along with the 3 hours of serverless, you probably saw almost everyone reference stateful and stateless applications in the realm of serverless. And As you can imagine, like dealing with state with serverless can be complicated. But in this next session, Rodric will be showcasing a simple solution to a complicated problem for not only stateful serverless, but stateful APIs. Rodric, how you doing today?
I'm doing well, thanks, Jamie. Good job organizing this whole thing.
Yeah, it's been fun from beginning to end, and I'm really happy with all of the people who've been asking questions. So definitely, everyone keep it up and keep asking questions in the chat, and we'll be sure to have Rodric answer them by the end. Rodric, I will go ahead and leave it up to you.
All right, thank you. So I want to just recap a little bit of what we've heard today. I think it's been a lot of information that was packed into 2.5 hours. And I think, I will have to watch Jeremy's talk at half speed because that was a lot of stuff and it went by really fast, but very clear. So thank you, Jeremy. And really thanks to all the speakers. If this is your first time really learning about serverless, I hope you've gotten a good taste of what it's like. And if you're interested in sort of going deep into the technology, I hope Arjun's talk really tempted you there. And if you're a pro and you sort of were looking for pro tips, I think the last talk really nails it. What I want to talk about in the next few minutes is where does this all leave us? And I was capturing sort of quotes from all the speakers as we went along. Right? I ended my talk with the serverless slide. And I talked about serverless being about focus. And really this comes through in a lot of comments you heard through the talks. It's not just functions, it's entire applications. Build quickly, you can innovate faster, you can shift your ops team to do more automation. So you're extracting more value out of your organization. And really this focus translates to a lot of value creation. And that value creation is really what we're all about as developers. We have ideas. We want to translate those ideas into tangible products that we can share with others, whether they're web services or applications for mobile devices. I wanted to just also recap some of the serverless benefits you heard about and make sure this goes home with you. And I think there were 4 key themes of what serverless benefits really embody. One is this whole reactive nature of serverless and functions as a service being able to react to events. As events come in, you want to consume them, you want to process them. There's synchronous, there's asynchronous, but it's really about the rich ecosystem of events that you can consume and the agility that you could do that with when you're talking about serverless computing. This whole ability to just massively scale without having to think about it. I mean, your applications can just go from 0 to thousands of concurrent API calls within seconds. And that's just amazing. Security is another aspect. It was touched on a little bit, but not very explicitly in some of the talks. So maybe this is something we focus on in future webinars. By doing less, you're shifting the burden of securing the server, securing the kernel, securing the runtimes to the cloud provider. This is a whole lot of complexity that now is no longer your responsibility. And lastly, this whole pay-as-you-go model, a utility-based model. I think Jeremy gave the reference to electricity, right? When your lights are off, you pay nothing. And this is very powerful in that you now have supercomputing power available to you for very, very low cost. And to give you a sense of that cost, right, it is possible to essentially run thousands of functions within seconds, and even millions of operations would cost you less than a quarter on almost all of the public clouds that you've heard about today. And it's not that it's just cheap, it's that there are enterprise use cases that have been published by Amazon and others. Here I'm listing some that are available from AWS. And these are companies that you would recognize that are essentially adopting serverless, and small teams within these organizations are essentially re-architecting and re-engineering key components with small teams and being able to deliver value faster. But now imagine you're a developer and you have an idea. You have the same kind of computing power now available to you for very low cost and incredible agility in terms of being able to deliver these applications. And to give you a sense of growth, right? In 2015, there were roughly 2 billion serverless functions processed a day. And today it's over 2 trillion. And that's exponential growth in just over 5 years. And that's amazing. But as much as this is, and as big as that number looks, it's still a tiny fraction of all the computing that's happening in the cloud today. So it means there's a long way to go. And I think some of the challenges and some of what you've heard about from the previous speakers today show you or hint at why we're sort of not all there yet. But I think serverless is easier. It's easier to develop applications. It's faster to develop applications in this model. And so I think it's also desirable, calling back to some of the things I pointed earlier, where there's a lot of job growth and demand that comes from these job opportunities coming in the near future from developers who aren't experts in cloud development, who aren't experts in distributed systems, but who learn how to code or who can code. And so now you're giving them the ability to essentially be able to access that computing power in the cloud. And so in that way, just like Jeremy ended with non-serverless is inevitable, serverless itself is also inevitable. And at Nimbella, our vision is to essentially make the serverless cloud beautiful. Our company, Nimbella, is essentially a beautiful cloud. That's why we named the company. And our entire focus is on the developer experience being beautiful. And what I'm going to show you in the next series of slides, and I highly encourage participation in what I'm about to show, you'll be able to, for example, create an account within 60 seconds, and you'll be able to deploy an entire application, not just a function, not just an API, but an application that you can interact with, that you can share with others within a couple of minutes. And it really boils down to one construct that we've essentially focused on in terms of how you interact with the Nimbella cloud, and that's deploying an application. And by doing that, we essentially allow you to build complete applications easier and faster. And a complete application, to me, includes state, because fundamentally, when you're interacting with users, whether it's on a mobile device, whether it's on a web application, or any kind of API that you're going to provide, there are aspects of state that you might need to handle, whether it's the user identity, whether it's Stripe payments and payment authentication flows, or it's just the data that you're trying to operate on. And I'm going to show you a couple of examples as I go along in the next few slides. And what Nimbella's view is, it's not just functions as a service, because functions as a service is really about compute. But if you look at a computer, it's about compute, it's about networking, it's about storage. It's about lots of components that have to work together to deliver essentially an engine that you can build applications on. So functions as a service is one aspect of a larger equation that allows you to build applications for this serverless model. And at Nimbella, this is what we focused on, essentially this integration between compute, networking, and storage, and making it available to you so that you don't have to think about it. Just like with functions, you just ship your code and it just runs. We want the same to be true for storage and for networking. And this concept of deploying a stateful application has several features that I wanted to call out. And you're going to see these very clearly in the next few slides as I show a couple of demos. The deployment of a serverless application, essentially your project, is repeatable. That means you can share it, you can commit it to GitHub, you can share it with others. Other developers that you work with can have their own deployment, and it's identical to what you're running, but it's in their own namespace, so it doesn't collide with yours. We're talking about entire applications. That means setting up everything from your domain name so that your application has a dedicated URL that you can share with others, managing the SSL certificates so that you actually have a secure connection to your application, the compute, the storage, and there's many levels of storage. And here I'm going to talk about two specific kinds of storage that we have available today for you to essentially just be able to build applications. And you'll see those in the next few slides. And manifestless to start. I think in a couple of the earlier talks, you saw that you have to sort of create applications, and to deploy them, you write a manifest, which works with the deployment tool. It's kind of a gatekeeper in the sense that I can't write a manifest from scratch. YAML is usually a language for these manifests. I can't keep track of what I need to do to sort of write my manifest from scratch. So typically you want generators for them. But if you just want to have an idea and you just want to deploy it, you don't want the manifest to get in your way. And so we've removed essentially all friction to being able to deploy the application. And the applications I'm going to show in the next few slides are manifestless, but they deploy an entire application that has a front-end component and a back-end API. It interacts with storage, and it all works out of the box. And so I wanted to show this using an example. I've got a couple of examples for you here today. This one is a page visit counter. So if you imagine what a page visit counter is, essentially it's a web page. You visit this URL, and it will tell you are number 5 or 6 or 7, depending on where you are in the timeline of the application. And this page visit counter is available on GitHub. It's one of our demo projects that you can deploy right out of the gate. And you'll be able to follow along. And if you're tempted, I encourage you to actually try our sign-up process. And by the end of this talk, you'll have deployed your application. And I encourage you to share your links to your deployed application in the chat. So what comprises this application? It's your code and just your code. What I'm showing here is essentially the entire project. There's nothing else to this project, and you can go look in GitHub and confirm this is true. There's 2 functions. Here I've implemented them in PHP, non-Node.js. And these functions, one essentially updates a counter. The other tracks some information about when this page counter started. And then there's my web component. There's an index.html page. It's essentially my web UI. It's very simple. It's written in pure HTML, and essentially presents you with the UI that I showed you earlier. But to implement this application, I actually need storage, because to have a counter means I have state. And to deploy this application with the UI aspect, I need to store it somewhere, and I need to serve it from essentially content delivery network or some model that allows its delivery of the content everywhere. I did something maybe gratuitous in this application where I also stored information about this application in terms of when it was deployed to an object store. So I'm using several aspects of the Nimbella provided services right out of the gate to have my counter and to be able to track individual users and to be able to store information about when the site is deployed. I don't have to worry about the compute, the data store, and the object store. If you look at this code in GitHub, I'm not going to show it here. It's fairly straightforward, and it's highly portable. As Rob had pointed out, the code that you write tends to be very simple, and that makes it highly portable. But what makes it interesting is that now I have an application I can share, and in fact, I have shared this code on GitHub, that you as a Nimbella user could deploy right out of the gate. And so if you wanted to deploy this, it's 3 steps. First, you need an account. And so if you already have an account, then it's 2 steps for you. And our sign-up process is fairly easy. So you go to nimbella.com/signup. You can sign in with GitHub. You can sign in with an email ID. And within 60 seconds, your account is fully provisioned. There's essentially a dedicated cloud ready for you. And that includes compute resources, data storage, and lots of other abstractions that we've provided that present value to the end user. And I'm going to come back to those in a bit later. So if you're going to get started, I encourage you to do that now. And I think, Jamie, you're going to share the links in the chat. I'm not monitoring the chat. Second is go into our workbench. This is so that you can actually deploy this application without deploying or downloading any tools to your machine. You can deploy this project right out of your browser. And so when you complete the sign-up process, you'll land on a page that looks like the screenshot that I'm showing on the screen. And somewhere towards the bottom, there's a link that says, click this link to go to the workbench. And when you do that, it'll actually bring you to our workbench. I'm going to show you a screenshot on the next slide. And from there, you can actually do your project deployment. If you want to continue using the Nimbella Cloud and you want to advance in your development, then you would go on and download the Nimbella CLI, and the instructions on that page will tell you what to do. So your final step, and this is the key step, getting back to our key intrinsic for working with the Nimbella Cloud, is deploying. And so from your workbench, you can type project deploy and just provide the link to GitHub, which is where this project is hosted. And what you'll see is this application will deploy, and you'll get a URL, which is unique to you. And I'm going to show you mine in a second. And your application is ready and deployed. If you've just signed up, keep in mind that DNS propagation takes a few seconds, sometimes a few minutes. And so if you hit that URL after you've deployed this application and you get a 404, give it a couple of minutes and retry, and you'll see what I'm about to show. So the screenshots here are essentially showing the workbench on the left and the deployed application on the right. So project deploy, and you're done. That's really it. And what we focused on is essentially making it easier and removing a lot of gatekeepers for getting started. And if you hit this URL, bit.ly/webinar hello, I believe Jamie is also sharing that link in the chat, then we'll be able to visit this URL later and see how many attendees from today's session have visited the page. post your visitor number in the chat as well. And so what's happening under covers is lots of functions are running, but they're all stateful. And even though this is essentially a distributed concurrent counter, I'm not worried about how the state is being managed. And under the covers, what I'm using is essentially a Redis key value store, which has atomic operations, and that allows me to essentially update the counters and work without me having to worry about any of the underlying synchronization otherwise. So what you didn't have to do if you followed along is you didn't have to register a domain, create a certificate, and make sure your SSL certificate is up to date. You don't have to provision any servers to serve your HTML content. There's no servers to run any of your compute functions, just like with functions as a service that you saw earlier. In the workbench, you can type nim activation logs. Nim is short for Nimbella. And you would see, for example, access to all of your activations that you've run. If you've used this application, you can see your logs. And there's scaling. So I don't know how many users are essentially hitting this. We can do a load test for fun later. And you get automatic scaling for free, as others were saying. The integrated storage, object storage, all of that is just there out of the box. And it's really about this hyper integration that delivers an exceptional developer experience. And this is what we're about at Nimbella. We have a number of more sophisticated projects. So if you go to nimbella.io, I'm showing a couple of screenshots there. There's some other applications that we've built that do more interesting things with state and object storage and object management. The OCR demo, for example, is optical character recognition, where you can take screenshots of images, dump them in your browser, and you can do many at a time. And each function tells you how far it is in processing the application. The models for analyzing the image and recognizing characters are optimized for you in the system so that you're not constantly loading and reloading a pre-trained machine learning model to do the inference. And then at the end, you can see the translated text. And for fun, you can do text-to-speech and actually have the browser read it out to you. We have a trade demo application. We have a chat room and some others. And all of these are available on GitHub. You can go to our organization, Nimbella/demo projects, and you'll see all of the applications there, all with instructions for how to deploy them with our deploy command. So I want to present you with a fun challenge. So if this is, your introduction to a serverless journey, you're tempted, you've been wondering how to get started, or you are somewhat advanced in your coding and you're sort of interested in doing something fun, I thought, what can I do here? So I wanted to build a single-page stateful application, serverless, of course. This one I implemented in JavaScript. Tends to be a bit more popular when you're doing web front-end stuff. Not necessarily the only language, of course. And so I thought, what can others do to make it better? So I created this application, which is a QR code generator. If you have a smartphone that's capable of scanning QR codes, hold it up to the screen, and it should open up a link to you. If you don't have a QR code reader, I'm going to show you the link, and you can actually read the text to see what's there. So if you follow through on this challenge and send a pull request to my repository, I will send you some prizes. The link is bit.ly/I-want-a-prize. And so if you participate in this challenge, I think you'll learn you'll learn a bit. You'll also interact with the Nimbella Cloud, and we'd love your feedback. We'd love your feedback on your experience, what it was like to actually build the application, and the stateful abstractions that we actually added to the programming language and the environments that you're working with. So what does this application do? Well, you write some text into the text box, and you click generate, and it generates the QR box. To make it stateful, I'm storing the images that are being generated. And this application essentially has a single API endpoint. It's called QR. And this screenshot is Postman. I'm showing the URL for my application deployed to the Nimbella Cloud and how you run it. You pass it a parameter, which is the text you want to encode, and it returns a result. And you'll see in the result down here that there's an image, which is actually hosted on Nimbella.io, but this is a dynamically generated image, and it corresponds to the text that you provided the API with. So if you scan it, you'll see the text. So this is a simple application. It has a single API, has some HTML and JavaScript on the front end, and I'm using the Nimbella object store to essentially create and store the images. You can develop this locally. You can test it in the cloud. The developer experience I find so convenient that I hardly ever really develop locally anymore. I just write code, deploy, and just test. And you can do that in a number of ways. So if you try this application, there's a number of improvements that you can make to it. And so scan the link, go to bit.ly.com/I-want a prize, and you'll see some instructions there for how you can actually improve this better, use the stateful aspects of the services. And so open a pull request, and I'll follow through. So really, your serverless journey starts with just one function. And with the functions playground that I showed earlier, and I was monitoring activity, we got a number of, I think over 100 people tried, or over 100 function activations playground happened within the first 15 minutes when I showed this, is really that showing you the convenience of essentially starting with the Nimbella cloud, but really starting with serverless in general, because it's about simplicity, it's about focus, just your function, and that's it. You can turn a function into an API almost instantly, and that often opens up a lot of opportunities for where you go next. Our goal at Nimbella and our mission is really to make the cloud easy and to make it accessible so that your development is really at the speed of your innovation. As fast as you can imagine, we want to be able to allow you to essentially develop, deploy, and share your applications with the world. We want to remove as many gatekeepers as possible and make it accessible to developers of various skill sets. We call our cloud serverless because on our cloud, if we're successful, we will never allow you to provision a service of any kind. The only services you get are the ones that are completely packaged with the platform to allow you to build complete applications right out of the box. You can never say, hey, give me a container, I want classic service, because I think in the end, if you think about serverless and you sort of be serverless, you adopt serverless fundamentally, you end up with a different kind of architecture and a different kind of application. And it's easier to do that when you're starting fresh. And when you're migrating from existing applications, it's important to sort of have a gentle migration path. So we're looking at ways of sort of introducing gentle migration path for lots of legacy applications and enterprises that are essentially still too early, essentially, in their serverless cloud journey. They can't quite make that leap. And it's understandable why that is. But there's a gentle migration path that eventually gets you to serverless. And so, quite simply, I think with Nimbella or with serverless in general, it's really about creating, it's about building, it's about running your applications, not thinking about infrastructure. That's somebody else's headache. And in Nimbella, we're happy to sort of make that our headache. So I'm going to conclude there. You can get started, as I said, on Nimbella.com/signup. I want to thank everybody who has attended. We've had, I think, many attendees I was monitoring over the chat earlier, so thank you for your questions. I want to thank all of our speakers, our community supporters who made this possible, and especially to Jamie and Yulia, who is not here, but part of our marketing team that made this possible. Jamie, over to you.
Rodric, hey, thank you so much for finalizing that 3 hours of serverless. We only just went like a little bit above 3 hours, so we stayed kind of within our timeline.
Great.
So we actually do have a few questions. So let's see. Okay, here's a question for you. How to design serverless to be cloud agnostic?
Right. So I think the way you do that is you have to think about it from the start. There's a couple of approaches. One, if you're deliberate about how you design your application, then you build it to be essentially cloud agnostic from scratch, which means you don't rely on services that are only available on one cloud. That tends to sometimes be a challenge, and you sort of should reflect on the reasons you want to do it that way. Cloud portability is really what's important. And if it's just your code, a lot of the services that I talked about from Nimbella are available on every other cloud. And it's really that integration that becomes hard. Part of the way we're doing it in Nimbella is to essentially provide and open source a lot of our technology. Nimbella, you've heard about Apache OpenWhisk earlier. It's part of the underlying stack that we run. There's lots of other open source technology that we integrate. And we're making it possible to essentially deploy an Nimbella cloud instance on any cloud that you want, whether it's Google Cloud, whether it's Amazon or Azure, DigitalOcean, IBM. We essentially want to be able to let you replicate that Nimbella experience on any cloud, and it's backed by open source. That's one way of essentially saying my code is cloud agnostic. And if you look at the code that I shared, a lot of what you see there is not specific to Nimbella. And this is essentially also highlighting a point that Rob made earlier. What really ties you in and what makes you not cloud agnostic is when you start using APIs that are unique to a particular cloud and making them essentially intrinsic parts of your application. Then it's very hard to essentially divorce. But if you approach it cleanly from the beginning and think about what parts really need to remain cloud agnostic and what parts you really need to go all in on a particular cloud because of value that it creates for you, and I think the choice is easier. For us to be cloud agnostic really means to be open source, to make it so that you can take your code, you can take this cloud and run it anywhere.
All right, good answer. So as a developer advocate, I get this question very regularly, and I'm definitely curious to see how you would answer it. So why should we opt for Nimbella versus other serverless platforms such as AWS, Azure, and all that type of stuff? Like, what would be the benefit of going with Nimbella?
I think it's complexity. If you followed along and you tried those 3 steps earlier, I would challenge you to do the same and as much time as it took you on any other cloud. And that's really what it's about. Serverless is about unlocking value. And it's not that you can't do this on any other clouds. And Nimbella itself is actually running on those clouds. We're running on Google. We can run on Amazon. We can run on Azure. And the value that we're providing is essentially hiding the underlying complexity. We're automating a lot of what you shouldn't have to do, right? The serverless promise is about focus. And so Nimbella is really hyper-focused on the developer experience and delivering that beautiful experience to developers so you can just build. You know, I don't want to call out Amazon sort of okay. If you log into the Google Cloud and you go to the console, you'll get lost, right? Where do you start? Do the same on IBM Cloud, where I used to work. It's the same kind of experience. Do the same on Amazon. Dashboards are full of potential services that you could use. Where do you start, right? And so if you're just thinking, I have an application, I just want to put it on the web, how do I do that? It's not that you can't do it on any other cloud. It's that you can do it faster on our cloud. You can do it better in terms of your productivity, and that's what we're essentially aiming for.
Yes, okay. All right, so I got another question for you. So with the value of serverless, you know, is the value really only for like enterprise grade level companies? Is it really only for startups? Is it a mixture of both? In your opinion, like, you know, who really gets the value from going serverless in those 2 scenarios?
Yeah, I think that's a very easy answer. Everyone. You know, I think everybody would be at a different point in their serverless journey, right? If you're an enterprise, then it's very slow potentially to essentially migrate existing workloads to serverless. But it's happening. I showed you a number of use cases earlier where the digital transformation is happening incredible speeds because of serverless. If you're a consultant or if you're a developer who's just building applications or an entrepreneur and you're trying to essentially deploy applications for your startup, you can do it a lot faster with serverless. Steady is one of my favorite startups. Zach Cantor is the CEO and founder, and he talks about how they've gone all in on serverless on AWS, and the incredible value they derive from that. And so it really spans the gamut from startups to enterprise. And that's the beauty here. It's this incredible computing power that's available to everyone. And so by reducing the barriers to entry, by making it more accessible to even more developers, I think this is the beauty of what serverless promise really is about and why I believe it's inevitable.
Makes sense. Well, Rodric, thank you so much for giving that presentation, talking about stateful serverless, and also answering all the questions that I provided. So we're going to go ahead and wrap up this presentation for the 3 hours of serverless conference. And as I stated at the beginning, we are providing a certificate for every single person who has participated in this webinar. So if you are interested in actually getting your certificate, so here's what you got to do. All you have to do is go to nimbella.com/Slack. What this link will do is that it will redirect you to Nimbella's community Slack channel, where you can join us, ask questions about any sort of thing with serverless, but you can also go ahead and jump onto the e-certificate channel. And in that channel, you can go in there and make a request like, hey, I participated in this conference. May I please have this certificate? And once you go ahead and join our Slack channel, you can go ahead and do that. And if you decide to join our Slack channel and participate, I also recommend, if you have not signed up for Nimbella Commander. If you've not signed up for, if you're not signed up for the serverless platform, not only do we have a free tier that we provide, we are also providing a pro tier for 90 days for free. And if you are interested in that, all you have to do is follow this bit.ly link, which I will be posting in the chat in a little bit. Go and do that. So if you check the chat right there, we will get you set up with the pro version of our serverless platform. All right. So other than that, yeah, that concludes the entirety of 3 hours of serverless. I would like to thank every single person who participated, whether you were a speaker giving a session, whether you were a person just either watching or asking questions in the comment section. We're thankful for every single person who was a part of this. And I know that this Nimbella doing conferences will definitely not be a one-off thing. I'm definitely looking forward to doing more conferences in the future like this and getting more community engagement. Rodric, do you have any last words you want to say before we wrap it up?
No, this was great. Thanks again.
Cool. Well, hope everyone has a great rest of the day.